Good morning and welcome once again to the International Workshop on Future Communications, organized by the Singapore University of Technology and Design. My name is Wayne Chan and it's my pleasure to be your host once again. Now we have an exciting program lined up for you for day 2. We'll be starting off with Professor Vincent towards 6G wireless communication networks, vision, enabling technologies and new paradigm shifts. This will be followed by Professor Kaixue, and he'll be talking about generalized multiple tanks and applications for silicon-based RF wave IC. We also have Professor Kountouris, who will bring us through rethinking communication theory for wireless network systems. And finally, we'll end off our day with Professor Lin Dai, and the topic will be random access for machine-to-machine communications, connection-based or connection-free. Now, today's event would not be possible without our kind sponsors and partners. A big thank you to Huawei International Private Limited, MPix Innovations Private Limited, Roder and Schwartz Asia Private Limited. And we also want to appreciate the support of the IEEE Communications Society. Now, for today's sessions, we have a schedule packed with lots of really great content. And to help you make the most out of this event, we're going to have to be very mindful of time. So please don't be surprised when you hear this chime playing at the end of some of our talks. There it is. That's just a reminder to our speakers that their allotted time is up. So don't worry if you hear this. There's no need to adjust your computer settings. That's just a reminder about time to our speakers. Now, if at any point you have any questions you'd like to ask our speakers, please feel free to post them in the Q&A section, all right, or via the chat function, either one. The Q&A section or via the chat function, we'll be channeling your questions to our speakers. And now, to kick things off, I'd like to introduce our first keynote of the day, titled Towards 6G Wireless Communication Networks Vision, Enabling Technologies and New Paradigm Shifts. Now, 5th generation wireless communication networks are being deployed worldwide, and more capabilities are in the process of being standardized, such as massive connectivity, ultra reliability, and low latency. This talk will review recent advances and future trends, and to bring us through all of this is a Michael Henry Strater University professor at Princeton University, with recent recognition of his work, including the 2017 IEEE Alexander Graham Medal and honorary doctorates from several universities in Asia, Europe, and North America. Ladies and gentlemen, let's welcome Professor Vincent Poor.
Thank you very much, and good morning, everyone. Very pleased to be here to speak to you this morning. Let me see if I can share my screen. I need permission to share my screen, actually. So I see that the host has disabled that, but it would be nice to be able to share my slides. So
yes, we have just put that function on, so you should be able to share your slides.
Yep. Thank you. Okay, good. There we are. I hope you can all see my screen now.
Yes, okay, you can see your screen perfectly.
So thank you very much for that kind introduction, and good morning, everyone. It's nighttime in the East Coast of the United States, but I know it's morning there. And I'm very happy to have this opportunity to speak with you today. I'm going to apologize in advance for my voice. I have a bit of laryngitis this evening, but I think I'll be able to get through my talk without much trouble. So as was said, we are currently deploying 5G, and of course there are still many things to be done to bring 5G to its potential. But today I want to talk about 6G, and of course this is we're thinking ahead almost a decade when we start thinking about the next generation of wireless. I know yesterday some of the talks also touched on some aspects of 6G, and there will be some repeat of some of the things that you learned yesterday, but I hope I can put it all in perspective in a different way. What I'm going to talk about today was published in a paper in Science China in January earlier this year. And that paper, and I'll just show you on the next screen, that paper had a large number of authors. So what I'm going to talk about today is really a consensus of many, many different perspectives about 6G. And I would encourage you, if you do, or if you are interested, to take a look at this paper, because it goes into a great deal of depth on some of the things I'm going to just touch on today. Also, I'll just point out that there are many people here, I'm sure many familiar names to many of you here on this author list. You know, they, all of them have their own inputs to this, and they're experts in many different aspects of wireless. I'm only an expert in some of the areas, so I'm going to touch on a lot of things, some of which I'm really not expert on, but I'll try to do my best to cover the material in enough depth so that it's understandable to all. So here's an outline of my talk today. First of all, I'll give some motivation for 6G. Then I'm going to talk some about performance metrics and application scenarios that we might expect for 6G. I'll mention some of the enabling technologies. This is where I'm a little more on a little more firm ground, because this is where I do most of my research. I'll talk about some of the new paradigm shifts we can expect to see in 6G. And then I'll wrap up very briefly with summary. And then if we have time at the end, I'll be happy to take questions. So let's start with a little motivation. So first of all, what do we have in 5G? So 5G, as I said, is really just now rolling out. So there's some major things beyond 4G that we get for 5G. One is enhanced mobile broadband, data rates up to a gigabit per second. Massive machine type communication. So one of the big advances in 5G, of course, is the fact that many of the users, if you will, are not human beings, but rather they are machines. So the number of possible users grows dramatically when machines can be terminals on the wireless network. And then part of the enabling of machine type communications is the development of ultra reliable and low latency communications. And I'll say a bit more about this going forward. So some of the key technologies that have been introduced for 5G, one is millimeter wave, of course. We moved from microwave. We've included, in addition to microwave, we've included millimeter wave communications. Massive MIMO, that is massive numbers of antennas on base stations in order to get much higher throughputs, and ultra dense networks, that is networks where we have many, many terminals in a small space. Now, so why do we need 6G? Well, even though 5G has achieved great advances, there are many requirements that we might look forward to in 2030 when 6G is going to be rolling out. So in addition to guaranteed latency, which is being provided by 5G, 6G is going to require high time and phase synchronization accuracy. And I'll talk a bit more about that later. Also, we're going to look to have 100% coverage everywhere on Earth and sub-centimeter geolocation accuracy. This is to support things like robotics and factory automation. And then there are going to be other applications, 3D video, virtual reality, augmented reality. These are going to require terabit per second level of transmission data rates, while 5G can only provide gigabits per second. Now here, you know, when I first got into this business, 30 years ago or more, the idea that you could support gigabits over wireless was like a pipe dream. But today we have gigabit per second wireless, and I'm confident that we will achieve terabit per second as well in the future. And then, of course, one of the big stories of wireless today is the fact that end user devices collect data, and there's tremendous amount of data out there, many different scenarios and all kinds of services that can arise. And so 6G will be a time when artificial intelligence will really come into its own in wireless networks. So again, just continuing a bit on the same theme of why we need 6G. Well, you know, up to 5G, traffic has been dominated by video, right? That's really the big, where most of the traffic is. And in 6G, there'll be other applications. So network control of robotics, okay, for example. This is going to create new challenges. For example, you'll have many robots in a typical application. They have to share control information, and that's going to overburden centralized controls. So distributed control systems using AI are going to become a necessity in 6G. When it comes to machine type communications with robotic applications. So what are some of the performance indicators that we're going to look for in 6G? Well, as I already mentioned, peak data rates of a terabit per second. So, you know, another 3 orders of magnitude beyond 5G, which seems almost impossible, but I'm confident that we'll get there. Very high connection densities, 10 million devices per square kilometer. These are not people, these are things. Very tight latencies, less than 0.3 of a millisecond in order to control things very precisely. Energy efficiencies up to 100 times what we have now, and spectral efficiencies up to 10 times what we have now. Positioning accuracies will need to be very tight. Indoor positioning less than 10 centimeters, again, to support robotics and things of that sort. Outdoor positioning on the order of a meter. This is to support applications such as automated driving. So what are some of the applications we might expect in 6G? Well, first of all the things we're doing in 5G, we're not going to go away. I'm sure many applications will arise over 5G capabilities, but there are going to be also a lot of new scenarios. One is human-centric services, that is, services that are designed to take advantage of or to cater to what humans need, privacy, other things, rather than what the network needs, which is speed, bandwidth, and so forth. Industry 4.0 and robotics, I've mentioned that already a couple times. The increasing use of wireless networks in managing factories to increase efficiencies. I'll say a bit more about that as well. And then convergence of all the types of things that happen over a wireless network. Communications, of course, computing, I'll say more about that, control, localization, and sensing. So a whole host of types of systems, applications will need to take place over wireless networks, and they have to converge to do so. Space, air, ground, sea integrated networks. I'll discuss this again a bit later. This is to provide universal coverage. And then distributed AI, things like federated learning and things of that sort, where artificial intelligence is distributed out into the network in order to optimize it in various ways. And I'll talk a bit more about that as well. So just some examples. One is cloud virtual reality. So of course, I think you know that virtual reality is a simulated experience that can either be similar to the real world or completely different. It can be augmented in some way. One of the most important aspects of virtual reality is computing power. It takes a lot of computation to support virtual reality. And doing that over a wireless link is a really big problem because latency, of course, because of human perception and so forth, is a big challenge of a cloud VR system. So this is a big challenge for bringing virtual reality to reality, if you will, over wireless, but this is one of the things where, in particular, terabit per second communication can be useful. Industry automation, I've mentioned it a few more times, but a few times already, but Industry 4.0 aims at enabling industrial production with improved flexibility, usability, and efficiency based on cyber physical system, of which the factories consist. So the physical system is the factory itself. And then on top of that is the cyber layer, controls, communications, sensing, and so forth. And Industry 4.0 wants to bring all that together to improve factory operations. So, for example, mobile robots, I mentioned before, remote maintenance, and plant asset management are some of the use cases that might come up here. Now, one of the challenges here is that factories, unlike wireless networks, factories have a very long shelf life. So, when we think about enabling Industry 4.0, we need to do that in brownfield, that is, in existing factories. So that means that there's going to be a lot of requirements for seamless integration of cross-industry technologies in this field. So let me talk now about some enabling technologies that will help support all of these applications. And one has to do with air interfaces and data transmission technologies. So one is multiple access. And now multiple access, or in general access techniques, really have been the key milestones to the evolution of cellular networks. If you look at the air interface, first generation was FM, so analog FM, for voice only. Second generation was TDMA, and it supported text. Third generation was CDMA, or a combination of CDMA and TDMA. So time division multiple access and code division multiple access, supporting web browsing online over wireless, okay? And then in 4G, we got to OFDM, which is where things have stayed for 5G. So orthogonal frequency division multiplexing. So 6G is going to require much higher spectral efficiencies and other efficiencies. And one of the potential multiple access techniques that might help define 6G is NOMA, non-orthogonal multiple access, which has been under study for a number of years now, and is actually a part of 5G standards, but not widely used in 5G. But the idea is that NOMA can allow users to take advantage of dynamic channel conditions to get an increased spectral efficiency. I think we can expect to see more of this in 6G. Actually, the idea of NOMA goes back a number of years, back to multi-user detection, which is a key aspect of NOMA. But in earlier generations of wireless, signal processing technology, and by this I also mean semiconductor technology, hadn't really advanced far enough to allow for the practical implementation of something like NOMA. Today, we have that technology, and certainly in 10 years, that will go even further. So now non-orthogonal multiple access is something that can be reality. Another aspect of the air interface is spectrum sharing. Now, we've been talking about spectrum sharing for quite a while, cognitive radio, but this again is something where technology and processing power and so forth can now allow us to do these things. So this is going to be very important in order to deal with the issue of limited spectrum that we're going to have with very high terminal densities. So we can do this in the unlicensed band, where we already have a lot of freedom in how we deal with technologies. So symbiotic radio, which goes beyond cognitive radio, is a recent evolution in spectrum sharing, which can enable massive access. And so symbiotic radio, unlike cognitive radio, symbiotic radio goes beyond and also allows terminals to share infrastructure and so forth. So again, we have very complex environments. And AI again is going to be an effective enabler to support the management of the spectrum in this very complicated situations. So, another aspect, of course, of wireless with so many different terminals and so many different applications is going to be the need to transact in the wireless network. And one way to do that in a trustworthy manner is to use blockchain. Okay, so in particularly for IoT, Internet of Things applications, when you need some security, blockchain is a good way to provide that security. So you can run smart contracts, for example, enforce various actions such as authentication and control. Okay, and so then this allows us to create trusted physical links to support a number of services and support something like, for example, federated learning. Big challenge with blockchain is latency, because as you likely know, if you study blockchain, there's a very high latency with blockchain. So in any applications where latency is an issue, blockchain has to be improved. And of course, there is research in trying to reduce the latency of blockchain. It's a trade-off, though, between some of the security features and latency. So this is an issue with blockchain. Also, scalability is another big issue with blockchain because, as you know, it requires many miners to create a trustworthy environment. And the more users you have, the more that needs to scale up as well. So blockchain is a useful paradigm, but it needs a lot of research, a lot of advances before it can be used in some of these applications. Another aspect of emerging aspect of the air interface is cell-free MIMO. So multiple antenna systems where the multiple antennas are to spread over multiple cell sites. So of course, the classical wireless network has a cell which owns certain terminals within its cell, a cell site which owns certain terminals within its cells and services them. In a cell-free architecture, there are no cell boundaries during data downlink transmission. And every base station that can see a terminal can be part of providing a service to it. Okay. Then in order for this to happen, you have to have cooperation among access points, and you have to overcome intercell interference. And again, here's a place where either pre-coding or multi-user detection can play a role. Some of the issues with cell-free MIMO are high implementation complexity. The more terminals you have, the more antennas you have, the more complicated the signaling environment you have, the higher the complexity. Also, there's a much higher load on backhaul and front haul. So you think about trying to coordinate all of these different cell sites or access points, and do that by uploading data into the cloud, doing the computations there. This is just going to create a greater burden on the front haul and the back haul. Okay, and of course, it all relies on getting accurate channel state information, synchronizing various access points and so forth. So there's a lot of challenges here. At this level, there are also a lot of other challenges, unmanned other potential technologies, UAVs or drones, in order to create hotspot coverage and so forth, reconfigurable intelligent surfaces to provide, to tune the radio environment and so forth. So there's a lot of exciting research going on in these areas, and some of it will find its way into 6G. Also, beyond the air interface, at the higher layers of the network, there are other aspects of new technology that will find their way into 6G. One is software-defined networking. So software-defined networks, of course, are able to provide flexibility in the higher layers by running on general-purpose hardware with software that can separate the control and data planes. So you can program the architecture, making it agile, cost-effective. You don't have to build new hardware every time you change the network structure. And it also allows you to upgrade on the fly. One of the key enablers of software-defined networking is network function virtualization, where you transform network functions into software, and then it runs on the top of general-purpose hardware, as I mentioned earlier. One of the pros of this is that this makes the network elastic and simplifies its management. Some of the negatives are there are still issues like mapping the physical to the virtual, how to integrate different functions and so forth. So this is a research area, but it's a very promising one for creating some of the things needed for 6G applications. Another aspect, emerging aspect for 6G is how we distribute computing throughout the network. So cloud computing, which is supported by cloud radio access networks, provides a lot of computing resources, all that you need really in the cloud. But data has to be uploaded from the network edge to the cloud. So this can cause high delay. So for some applications, this is fine. But for many applications, that delay is intolerable, okay? So some of the computing can be pushed forward toward the edge of the network to get lower latency. Fog computing looks at the use of multiple layers that interact with the cloud and the edge. And then there's edge computing, which is in standalone mode. That is, it doesn't use the cloud at all. It only does computations at the edge of the network. Okay, and this can work for many applications where data is already born at the edge. So computation can be done there too, taking advantage of the advanced computing power of edge devices. So, you know, this is, there's no one answer to how this architecture will shape up in 6G. There's just more flexibility. Different applications can take advantage of different properties of these types of computing architectures. So now let me talk about some of the new paradigm shifts that we hope to see in 6G. So 4 I'm going to mention. One is space, air, ground, sea integrated networks, which I've mentioned briefly before. The idea here is to combine satellite communication, drone communication, traditional terrestrial communications, and maritime communications into one integrated network. I'll say more about this in a minute. Another type of integration is across spectra. So today we have, of course, most wireless takes place in microwave band, sub 6 gigahertz. In 5G, we now have millimeter wave on top of that. For 6G, we're looking to build on top of that, moving up to terahertz band, and also to look at free space optical, things like Li-Fi and so forth. I'll talk about this again in a minute. Intelligence endogenous networks, where we use machine learning for network control and machine learning for resource management. So again, distributing AI out into the network. And finally, security, okay? And I'll talk a bit more about this. I'm going to dig a little bit into one aspect of security at the end of the talk. But there are enormous security and privacy problems that arise in the new applications for 6G. And I'll say a little bit about some solutions as well. So space, air, ground, integrated networks. So the objective here is to provide truly ubiquitous wireless communication services globally, So the advantages here are with satellite communications, for example, we can get seamless wireless coverage everywhere. Of course, it has disadvantages of latency and so forth. Drone communications can provide great flexibility, mobility, adaptive altitude, and so forth. The resources can go where they're needed on an adaptive basis. And then, of course, maritime communications, well, the oceans covered 70% of the Earth's surface. So maritime communications are very important if we're going to have ubiquitous coverage. Some of the issues that come up, well, how do you manage all of these different networks? They all have different characteristics, different quality of service characteristics, and so forth. So how to manage them all is a major issue. And then how do we route among all these different networks, particularly satellites and drones? Energy efficiency is huge, particularly for drone communication. Energy efficiency is a major issue. And then what are the protocols that we're going to use to transport data across these networks? Well, here's a place where software-defined networking can play a big role. because it can allow hybrid and hierarchical network control that it will allow us to flexibly use these kinds of networks together. Similarly, we will want in 6G to integrate across spectral bands. So the idea, of course, is we want to provide this ubiquitous high data rate coverage. And to do that, we're going to need to take advantage of all the spectrum we can get. So again, we know from 4G and previous that we get wide coverage at fairly low cost in the microwave bands. So that's the traditional cellular communications. In 5G, we've added millimeter wave, and with that we get wide bandwidth, high capacity, and we're able to look at much more densely packed terminals because of the narrow beams afforded by millimeter wave. Terahertz, which is just being considered now, gives even larger bandwidth, better security, easy tracking, and so forth, because again, very narrow beams and very short transmissions. Optical bands, of course, we're thinking about LEDs, using them to modulating LEDs for communication indoors, and it's easy to contain that kind of thing. So security is enhanced. It's much easier to control what's going on with optical signals. So some of the issues are channel modeling and measurement. We don't really know how the channels look, particularly at terahertz. If we're going to integrate it and optimize spectrum use, we need to have metrics for how to evaluate spectrum usage. I mean, to do optimization, you need some kind of utility function. And then just how do we manage all these resources? Okay. And now here's a place again where machine learning can play a big role, because the problem is just too complicated to think about optimizing in a more traditional way using analytical optimization. So this is, I think, where we're going to see another application of machine learning in 6G. Endogenous networks. Again, the idea is to enable 6G networks to incorporate intelligence and self-evolution capabilities. So one of the examples is, of course, two examples, of course, are the integrated spectrum integration and different network integration that I just talked about. So some of the advantages of adding intelligence is that we can use it to analyze what's going on in real time. What users are there, what quality of service do they need, and what are the environments that we have, what is the radio environment that we have to service those users. In order to realize things like stereo perception, which is a very non-traditional kind of optimization problem, artificial intelligence can play a big role there. Of course, decision-making problems like resource allocation in the factories and so forth. These are places where AI can be very useful, and just dynamically adjusting the network. So if you think about the air, sea, land network, dynamically adjusting where the traffic is, where it's going, depending on the environment and where the terminals are located, is something that can be done using intelligent networking. So there are a lot of issues. I mean, just thinking about creating a knowledge graph for a very complex network is a difficult problem. And how do we design the mechanisms that we want to use in order for networks to evolve? So there's a lot of work to be done here, but I think it'll pay off with a lot of efficiencies in doing things that we couldn't do without AI. Another big issue is security. Okay, and I'll just start out with AI itself. So there are a lot of security and privacy problems raised by AI. One of them is privacy. The data is often has personal data in it, the data that's used in training. And that data can leak through AI algorithms. So it's widely known that the privacy of data is compromised by machine learning. And also there's vulnerabilities in AI software that can be exploited by malevolent actors. So these are issues that have to be dealt with. And IoT devices themselves are problematic. So first of all, when you have a massive number of them, they can't necessarily all be authenticated. And so you might have malevolent or malicious devices participating in machine learning or other activities of the network. And due to the limited nature of IoT devices, these are not cell phones, these are sensors, actuators, and other lower complexity devices. They don't have the capability to support complex cryptographic algorithms like a cell phone could or a laptop. So some potential solutions, first of all, taking traditional cryptographic methods and replacing them with much more lightweight versions of themselves. So this provides lighter security. Another is efficient physical layer methods. Okay, and I'm going to talk a little bit more about that in just a second. And then finally, quantum-based methods where quantum technologies are being developed in parallel with the evolution of wireless networks. And so perhaps there'll be some quantum-based methods that we can take advantage of in the future. And then finally, I already mentioned blockchain, which is a way of enabling trust. Of course, it has its disadvantages as well, but again, research may overcome some of those disadvantages. So I think what I want to do now is to dig a little bit more into physical layer methods. I'll just go at a very high level, talk about that a bit more, and then I'll wrap up, and then I'll be happy to take questions if we have time. I see there's a number of them in the chat and in the Q&A. Okay, so let me just say a little bit about physical layer security and motivate it. Today, security is really implemented at higher layers of the network, typically at the application layer or the transport layer. And in current networks, it works well. That is, I think we can be confident that our cell phone or our laptop is pretty secure, at least in terms of the data communication capabilities. And we're completely comfortable using it, for example, for banking or other secure activities. So why would we need physical layer security? That's really a question. Why don't we just stick with what we've got? Well, a couple things I already mentioned, but let me just mention some of the good things about what we have today. First of all, there are no known feasible attacks. With a long enough key, your information technology is secure with cryptographic methods, okay? It's widely employed and tested. There's trustworthy authentication and so forth. Now, some negatives of standard crypto are that they're really built on unproven assumptions of the difficulty of computational problems, right? And so with the emergence of quantum computing, those assumptions may not hold true. Also, they're very computationally intensive in general. So as I mentioned already, IoT devices, for example, may not be able to implement standard crypto. And they require infrastructure, okay? So in some applications, the terminals are highly distributed with very light infrastructure, grant-free type access and so forth. So it may not be possible to manage crypto in some emerging network applications. Now, physical layer security is based on fundamental radio characteristics, that is physical characteristics of the radio channel, which can't be beat by computation, okay? So it's secured against quantum computations even. You can use the properties of the radio channel to generate key on the fly, so you don't really need infrastructure to generate or to manage key. And it's generally fast and lightweight. That is, the kind of encoding that you need for physical layer security is very similar to error control coding. So you don't need high complexity or at least complexity beyond that kind of error control coding for physical layer security. Now, there are some disadvantages. First of all, a lot of physical layer security techniques rely on some knowledge of the eavesdropper, of potential eavesdroppers, and what their channels look like and so forth. So these are areas where there are workarounds, but still a lot of work needs to be done to make this practical. A lot of the theory, like a lot of other information theoretic principles, is based on asymptotic theory, whereas most of the applications where this would be interesting is for low latency, ultra reliable low latency type applications where the block lengths are going to be short. Okay, so that means we need to work on physical layer security, which is based on information theoretic security. We need to work on these problems for short block length, non-asymptotic problems. There is work along those lines, but a lot more needs to be done. And then finally, unlike standard crypto, this is really not reality today. This is still in its infancy. It hasn't been proven in applications. And so a lot more needs to be done to make it work. So prime example, though, where we need this is in something like the Internet of Things, because the number of devices, the infrastructure, the lightness of the infrastructure, the low complexityness of the devices, and the short messaging and so forth, all the things about IoT are things that sort of work against standard crypto. So physical layer security is a way of securing something, securing Internet of Things type applications. Now, one thing to think about is that the level of security needed for IoT may not be the same as the level of security you need, for example, for banking or for some other very highly secure applications, right? So you can think about physical layer security as a way of providing best effort security in certain situations. So you can think about, like we think about quality of service in wireless, we could also think about quality of security as a parameter. And one extreme is, very high power crypto, and another extreme is physical layer security. And somewhere in between, we might do combinations. One might augment the other. So we have to start thinking about security as being something that's not necessarily bulletproof, but rather something that we do to the best of our ability, just like we provide quality of service to the best of our ability. So here's an example of what might go wrong if we don't secure our IoT networks. And this comes from a paper a couple of years ago from USNICS, which is a security conference in computer science community. And here we looked at an IoT application, and namely smart grid, where IoT devices are used to control high wattage devices throughout people's homes, so air conditioners, refrigerators, and so forth. So if in the US, and I think probably in Singapore, we have Nest, which is basically an IoT application to control household appliances, okay, over the internet. So what we looked at here was what would happen if botnet of the size of the Mirai botnet, which was a real botnet that got out a couple of years ago, and control 600,000 bots. If we could control that many water heaters that were on, say, using Nest, and turn them on or off instantaneously, and simultaneously, that would be like controlling a 3 gigawatt reactor, which is, it would be like switching on and off the largest currently deployed nuclear plant. This would be highly disruptive to the grid. I think anyone who is familiar with the grid, electric grid, knows that it has to be kept stable, and sudden load, either up or down, can be very disruptive. It can cause load tripping, generator tripping. It can cause cascading failures and so forth. So this is a real threat. IoT devices are not very secure today. I think we're fortunate that there really aren't that many of them yet, but someday there will be, and when they are, they'll be vulnerable. So we really need to start thinking about these things now. So what about physical layer security? Well, I mentioned, it can really offer best effort security. I think that's the way to think about it. there's a lot of things physically about wireless that cannot be attacked this way. And there's my ding, I think. So let me just wrap up quickly. So we have in message integrity, we can look at things like footprint, the fingerprints of wireless devices, physically unclonable functions, and so forth. We can look at biometrics, other things of that sort. And for message confidentiality, we can look at wiretap channel coding, so wiretap codes, and secret key generation, as I mentioned before. All right, well, since I've heard the signal, I'm going to just wrap up. This is my last slide. So what have I talked about today? Well, I talked about some ideas about 6G, some of the metrics and applications. Global coverage is one of the things we want. Enhanced spectral energy cost efficiency, better intelligence level. Some of the enabling technologies, we talked about air interfaces and transmission technologies, network architecture, things like software-defined networking. And then I talked about these paradigm shifts, space, air, ground, sea integrated networks, all spectra integrated networks, intelligence, endogenous networks, and some security issues and solutions. And I took a little bit of a deeper dive into physical layer security. So with that, I'll thank you. And I'm going to now, it looks like I have about 15 minutes. I won't take it all, but I'll start looking at the questions and see what we've got here. Okay. Let me just give me a second here, get back to myself.
Thank you so much, Professor Vincent Poor, for that presentation. And I'll be joining you for this Q&A segment. We've got quite a number of questions for you. Lots of members of our audience are truly interested to find out some of the more about what you have presented. We're going to start with this question from a person called PG Patil. And PG Patil would like to ask, how will 6G help in the privacy of MFG, I believe that's manufacturing plants, and ensure information security? Which is the greatest challenge implementing digital ideas in MFG? I'm assuming that's manufacturing, especially in pharma companies. What's your take on this, Prof?
Yes, well, very good question. Some of the things I mentioned already, I think will come into play. I mean, for example, if we think about using AI out at the edges of the network, one of the big issues, of course, is the privacy of that data. And one of the potential ways of protecting privacy is to use something like differential privacy in order to hide sensitive data. But that's not enough. We also have to worry about things like poisoning attacks on machine learning algorithms and so forth. And there are ways of defending against those, but certainly they're going to have to be built in to wireless networks before they can be used in a trustworthy fashion in manufacturing or other cyber physical systems. So it's an excellent question. I think there's a lot of research to be done, and I think it has to be done before we can really trust these systems. So.
Thank you so much for that answer. We have another question for you. This time it's from Shemuel Yerushalmi. And the question is, according to your opinion, how do 6G technologies help in preventing social and economic crises? Among others, can 6G help in predicting financial frauds, for example?
Well, I mean, I think let me just say that there's probably, if you think of 6G as a technology, it may not in itself be able to address that problem, but it may create infrastructure that allows, say, bank examiners or others to gather the data that they need in order to look for, for fraud and so forth. But I think actually fraud detection is probably something that's it's an application would have to be done maybe using data gathered by 6G network, but not necessarily using anything particular property of 6G. It's an interesting question. I think social, you mentioned also social issues. Right. I think, the distribution of terminals with all kinds of capabilities throughout society can certainly address social issues, right? I I mentioned the power grid, making it more efficient. Of course, a big issue is climate change, and making the grid more efficient is certainly a way to address that issue. And I think 6G can have a role there by allowing the deployment of sensors, actuators, and all kinds of other technologies that allow much greater efficiencies in the energy grid. So, that's one example. Hospitalization is another one. Of course, healthcare is a big social issue. And I think 6G, with some of the human-centric applications that it can support, sensing and so forth, I think can go away toward improving healthcare. And also senior, the well-being of seniors in our society. I think having 6G technologies, various kinds of IoT, can allow seniors to live in their homes longer and be safer. So I think there are a lot of social issues that can be supported by 6G capabilities. How they're supported, I think, will involve not just people like us, but will also involve social scientists and medical professionals and so forth. So.
Thank you so much. Some really good examples there. Thank you so much for expounding on that question. And we still have some more questions pouring in. This next one is from Neil Kundu. And the question is, how can the spectrum efficiency be increased 10 times? Will it require a completely new modulation and coding scheme? What do you think?
Well, one way of increasing the spectral efficiency I mentioned already, which is NOMA, non-orthogonal multiple access. So sharing the resources among multiple users. So that may not get us to 10x, but it could get us to 2 or 3x. Okay. And then to get the remaining, we have to look for other efficiencies, better coding. Certainly, if we can do security using more lightweight security, then we need less spectrum to deal with encryption and so forth. So I think all of these things can add up to spectral efficiencies. And then another aspect too is, looking at, just not only spectral efficiency, but using more spectrum, which I've already mentioned. That's not necessarily an issue of spectral efficiency, but it is a way of dealing with the fact that we just don't have enough spectrum to support this kind of activity. So terahertz, optical, so forth, these kind of things can also be part of getting the spectral resources we need.
Thank you so much, and we hope that answered that particular question from our audience. Next question is, with 5G, 6G, and beyond, will there be a tremendously increasing demand for data storage and security? What are the potential challenges in this area? What do you think?
Well, I already spoke a little bit to a couple of the challenges. One is, of course, privacy. That's a tremendous issue. Security of data is another one. Just securing data. We see even the most sophisticated corporations and organizations have trouble protecting themselves from cyber crime. So this is just going to multiply as we have more and more data. I think there's a lot of work needs to be done in order to make all of our cyber systems more secure. And this is certainly an aspect of it. As our lives become more data intensive. Our healthcare data, if it's all, in the US, healthcare data is primarily on paper. I know in some parts of the world, it's mostly now electronic. But as data like that becomes more electronic, it becomes more vulnerable. And I think, data about other aspects of our lives, not just our health, but our lives in general. There are a lot of private things that need to be protected, religious things and so forth. And the more and more data there is about us, the more we're going to have to worry about that. And I think the technologies is part of it. It's probably the biggest part of it is technology. I think that I would say that. Unlike some of the other things we discussed, this is really where technology is at the core.
Great. So there's some more questions for you. This next one is about dynamic spectrum. It says, for dynamic spectrum from sub 6 gigahertz all the way to terahertz, what is the implication on the hardware at the UE and base station?
Okay, so you know, the UE, of course, has to, the UE being user equipment, meaning the end user device, it has to be capable in multiple spectral bands. Now, not every device has to be capable for every band. I mean, your phone, for example, can still be a microwave phone. But for IoT, you know, when you have very densely packed networks, you might want to have the capability of using some radio and some optical communications and so forth on the same device. And in fact, I think that just in terms of, for example, your laptop could easily have, you know, multispectral capability. One of the spectra being LED communication, and another one being microwave or millimeter wave or so forth. So I think, you know, we're going to have to deploy multiple spectral bands on individual end user devices. Now, the infrastructure, that is the access points and base stations, I think is the term that was used, you know, they're much more sophisticated devices. So, you know, they can have multiple radios on them, of course. And I don't know that the same access point would really be necessarily multispectral. You might have small access points, which are terahertz access points, slightly larger coverage area for millimeter wave, and then traditional microwave cell sites. So I don't know how it'll work. Certainly the end users have to be able to respond to whatever spectrum is available. You know, the infrastructure can be a little more partitioned. We'll just have to see how that works out.
Great. We still have a bit more time, and another question from Zi Wei Chua. And the question is, what are the time signal accuracy requirements for time synchronization and reference? Time signal dissemination accuracy needs to meet the 6G network's low latency or time stamping requirements.
Yeah, so you know, I think these are still being worked through. I mean, we have a you know, another decade of research to work on these kind of things. But you know, I mentioned already, you know, 3.3 millisecond latencies, for example, and you know, submil and sort of 10 centimeter type of localization accuracies. Okay, so these kind of accuracies assume very tight synchronization, right? You just can't get them without that. So I don't know exactly how to translate that into synchronization, but I think the end application is really based on things like positioning accuracy and latencies, and so those requirements are going to drive the requirements for synchronization accuracy and so forth. I mean, an example for if you look at cell-free architectures, right? I mean, in order for that to be useful, if you're transmitting at terabits per second, the signals have to arrive from multiple base stations in sync. And if the data is going at terabits, that tells you right there that you've got to have very, very sharp timing accuracy in order to get that kind of synchronization. So it's going to be another multiple orders of magnitude improvement in what we have today. I think maybe that's a good way to phrase it.
Great. Great answer. And we have time for just one last question. This will be the last question. And this one is about health concerns. And it's from Wahajat Nasa. And the question is, what may be the effects of 6G on human health? What would you say that could be?
Well, I think I already addressed that. I mean, I think,
Mm.
you know, one of the great capabilities of even 5G and going forward into 6G is, health, body area networking, where you can monitor what's going on in your body, in real time. And it can be, downloaded to your cell phone for analysis and so forth, or it can be transmitted to your physician for analysis. So people with, for example, heart conditions, rather than being monitored once a month, they can be monitored in real time. And, data analytics can be used to let them know if there's some issue that they need to deal with. And that's the capability you can only get with a body area network. There's really no other way to do that. And then the other one, so I think that's, for certain diseases, I think it's a game changer, really, in terms of management and the kind of lifestyle people can lead when they do have those diseases. I think diabetes is another one, right? If you have the right sensing, you can keep track of that in real time. I think the other thing I mentioned was, aging in place. I think that's a big trend. I don't know in Singapore, but in the US, certainly that's a big trend for seniors to stay in their homes much longer. It's much less expensive than, being in a nursing home, and it's also much nicer. And I think that can take, I think, again, there's with IoT devices that can detect falls or things of that sort, or other issues that seniors may have. I think that's just a way of prolonging the quality of life of people well into their senior years. So I think that, it's going to have a lot of impact. It won't all be 6G. I think some of it will be 5G. I think it's already, some of these capabilities are out there, and it's just a matter of developing the applications on the infrastructure we have. Some of the ultra low latency might be helpful in something like robotic surgery, for example. So that's another sort of whole nother area of healthcare where I think there we might find it even in 5G. So.
Thank you so much, Professor Poor, for taking the time to answer all those questions from our audience. And of course, thank you, the audience, as well, for submitting all those questions. And we look forward to even more participation in our later sessions. Thanks once again to Professor Poor for that inspiring talk as well on 6G wireless communications network. Thank you so much.
Thank you all. Thank you all. Enjoy the day. It's bedtime here, so good night.
Good night. Good night. All right. And of course, that was Professor Vincent Poor, that very interesting presentation. Coming up next, we are going into generalized multiple tanks and applications for silicon-based RFMM wave IC. Now, radio frequency integrated circuits and MM wave IC play crucial roles in the modern wireless communication systems in laptops, smartphones, tablets, and more. But commercial silicon always faces issues of high substrate loss and metal loss. Therefore, a new methodology of multiple tank topology to cope with this loss issue has been proposed. This talk presents the proposed method and implementation from the fundamental concept and analysis to the new integrated circuits and system verification. And to elaborate on all of this is an awardee of the Chinese National Science Fund for Distinguished Young Scholars. He is also a fellow of China Institute of Electronics, a past associate editor, IEEE TMTT, and IEEE MTTS R10 coordinator. Ladies and gentlemen, let's welcome the Dean and Chair Professor of the School of Microelectronics of Tianjin University and the Director of Tianjin Key Laboratory of Imaging and Sensing Microelectronics, Professor Kaixue Ma.
Okay, thank you. Let me share the screen. Okay, can you see the screen?
Yes, we can see it really well.
Okay, let me start. Okay, thanks. Nice introduction from the presenters. It's my pleasure to be here and to give the talk presentation on the hardware design related wireless communication, for example, for Wi-Fi or short-range communication. And I take this opportunity to also to thank the invitation from the organization committee and also Professor Yu. And I think I just see the question from the Tony Quick about the what's the challenge, what's the issue brain if adopt from sub-6 GHz to terahertz. I think for the user end and for the base station, I think to adopt the very high frequency and a very high speed, the major issue bring to the hardware is the power consumption and also linearity. And there will bring a lot of challenges for hardware design, for IC design, as well as for the system integration. I think this topic will cover most of the issue we face from the circuit design and the system integrated level to see how we'll deal with this kind of a challenger problem. The topic of my presentation is generalized multiple tanks and applications for silicon-based RF and millimeter wave IC design. And I'm Kaixue from School of Microelectronics at Tianjin University. And my presentation includes the following parts. First of all, I will give the background, and later on, then I will introduce the single tank versus the multiple tank, and we'll see how the advantage we can achieve by using this kind of multiple tank technologies. And we'll use the multiple tank technology for the VCU and frequency divider application, and also introduce this kind of multiple tanks for amplifier design and also switch application. And we also adopt this kind of multiple tank technologies for transceiver SoC, and we'll also give some insight for the future applications. And we'll also share some other related work of our team, for example, for the Wi-Fi short-range communication and for 5G millimeter wave SoC development in our team. And finally, I will give the conclusion. And before, for any wireless communication system, before we start design, we need to do the product definition. For example, we design a short-range 60 GHz wireless communication. We need first of all, we need to consider the application scenarios. Based on the application scenarios, we can define, for example, the communication range and the coverage, power, operation, and also data rate. Of course, based on these kind of application scenarios, we also have the confinement of the front end. For example, the TXX power consumptions, the maximum bandwidth, channel and phase noise, linearity, and the severity of the spectrum as well. Of course, for the commercial application, we also need to consider the temperature range. For example, we need to cover minus 85 degrees to plus minus 40 degrees to plus 85 degrees. So this application environment requirement, of course, based on application scenarios, we also, from the user end, we need to have the baseband, which helps to define the I/O interface and the power constraints, and also modulation schemes. Of course, we also need to define the access schemes, delay constraint, especially for high-speed communication system. The latency has become a very important issue for 5G and also for 6G. Of course, we also need to have the ad hoc constraints. So by this kind of requirement, we also need to have the MAC and 5 layer definition. For example, ADC-DAC, we need to which kind of data rates to support this kind of communication range. I think these general pictures can give us an insight for any wireless communication system. What's a major issue we need to consider for our system design during our design? Of course, for this kind of wireless communication system, the overall constraints is this kind of IC chipset or this kind of solution. Does this cost matching to the application scenarios? This is very important, whether the market can accept or not this kind of the chipsets or the system. For our 60 gig design, we actually our targeted portable segments, which is in the range below 3 meters. And we support Type 3 and Type 4 mobile device use only single carrier modulation to save the power and the maximum bit rate to 2.5 gigabit per second. And of course, there's other applications for short range communication, and there's also other applications. I think this is based on the IWFC 802.11ad standards. During the time, the standard ongoing, and we carry on a lot of fundamental research for this kind of application. So for the portable device, the major consideration is the system has to have a battery efficiency. We need the circuit and the system have a low power consumption. Of course, for system, we need to have a low loss as well as, and also the size, which are crucial for the cost effective and also application. So the size is become very important for the IC design. So which kind of process we can select for the short range communication system? We do have a investigation. Right now, for the millimeter wave design, there are a lot of applications during the past several decades. It's actually based on the gallium arsenide 3-5 groups semiconductor process. But the commercial silicon is actually the most of a cost-effective way for mass production. And right now, the silicon-based IC dominant the IC market, about 90% of the total IC. So, which is widely used in the digital, analog, and sensor, and also RF and the millimeter wave in recent years. And it's also, for example, this widely used in the computer, smartphone, automobile, and also some space applications. Here we show the examples for the smartphone, which use a lot of low cost and low power, small size chipsets in the phone. So the overall power consumption and the cost become major issue for the portable device. So for the commercial silicon, we do have a number of process to be a good candidate. For example, CMOS process or silicon germanium by CMOS process or SOI process. Here we show the typical multiple layers silicon process. We can have a cut view of the process. This process of single poly 6 mental layers process. We can see there's a 6 mental layers from mental 1 to mental 6. So these mental layers we can fully utilize for the passive, for example, inductors, capacitors, or the interconnect applications for our IC chipset design. Besides the active device like the MOSFET or the diode, all these kind of active devices. So for this kind of commercial CMOS process, so for the silicon germanium, what advantage for the silicon germanium, which is also the one good candidate, because right now most of the process I think is based on 6-inch wafers, but CMOS the dominance is based on the 12-inch process. So for the very large volume, the CMOS process become very good candidates. Of course, the SOI process right now also have a 12-inch process, but the silicon, they use a high resistivity silicon and also have the silicon oxide box layers to reduce substrate loss. So for our consideration, we choose the silicon germanium for our IC design. but we also still face the same challenges. So for this kind of multiple layers, mental layers, we have a very good advantage, very good advantages for high-level integration. We can build multi-layers, inductors, passive device to shrink the size. But we also face challenges because we use a commercial silicon, which have the low substrate resistivities, normally about 10 ohm per square. So this compared to the high frequency, for example, millimeter wave design, like the Rogers substrate, the resistivity as high as up to 10⁻⁷ ohm per square meter. So this brings a lot of challenges for our IC design, especially at the millimeter wave frequency band. The substrate loss become a dominant issues, and beyond the substrate loss, another issue is the mental loss, because there's an ohm loss that generates. And let's see how the substrate loss affect our IC design at the millimeter frequency band. Here we show some paper we publication to demonstrate if with a low silicon substrate, 10 ohm per square, and without, we can see with this kind of ohm loss, substrate loss. So the insertion loss can be up to 10 dB. That means there's a 90% energy is become heat sucked by the substrate. So, and this kind of heat also become as a noise for our active circuits as well. So, so this kind of substrate loss become a major issue for our IC design. For example, here we show the bandpass filter design. The loss up to 8 to 10 dB is become a challenge for the filter design. And of course, this kind of filter also demonstrate as a passive device. If we use it for inductors or other passive elements, the mental loss and the substrate loss still have same issues for our IC design. So from this kind of investigation, we will become have this kind of our project motivations. So we see the high substrate loss and mental loss of commercial silicons. What's the issue caused by using this kind of high loss substrates? So the issue caused for RF and millimeter wave silicon-based circuit design will, first of all, we'll have a low quality factor for resonator or LC tanks, because this kind of resonator or LC tank is widely used in the filter, oscillator, and other matching network as well. So the second issue bring for this kind of disadvantages is a large insertion loss for the filter and the switch. If we build the switch, use this kind of passive, this kind of transmission line, use a high loss substrates, the insertion loss will become very large as well. And also, this kind of insertion loss will become a power issue. They will have a large power consumption and low efficiency for amplify. And if we use for the low noise amplifiers, we'll have more noise figure for our low noise amplifier as well. And then if we use this kind of issues for other passive circuit design, the loss also become an issue. And for the source signal generators or voltage controlled oscillator, and also frequency divider and synthesizer, the poor phase noise due to this kind of high substrate loss and mental loss will also bring to our design system. Based on this kind of investigation, we propose solution for the multiple tank-based circuit and topologies to improve or enhance the circuit performance. So before we start, let's choose a single tank as contrast to the multiple tank. Here we show the single tank is formed by inductor and capacitors and also the equivalent resistance. This have become a symbol for the equivalent circuits. We can do a simple analysis. For this kind of LC networks will behave as a resonator or LC tank. So the it will resonate at the resonance frequency. So below the resonance frequency Fx, as is behave as capacitive behaviors, and above the resonance frequency, it behave as an inductive response. So for the tank qualifiers of this kind of LC tank or resonators, will define as Q is given by this kind of equations. Is R divided by the also inductance based on this kind of equation. And after the simplification, we can see the qualifier is related to the equivalent resistivity, and also with capacitance and the inductance. So we can also do a simplification. The LC tank qualifier will be determined by parallel connections of the inductor qualifier and the capacitor qualifiers. So the maximum value will be determined by the minimum value of the qualifier, either inductor or capacitor. So this roughly discussed about the single tank. For the single tank, there's we can see we build this kind of LC tanks. We use a silicon substrate. We will use inductors. This the spare inductors we build on the silicon wafers. So the inductor, the Q, will reflect the energy stored over the energy dissipation. It will defined by the integration of this kind of equations based on the EM field. So the overall qualifier will give in this kind of equations, which counter in the silicon resistivities and also the parasitic capacitance of silicon oxide. So dominant loss for this kind of cheap LC tanks is from the inductors for the RFIC design. And the inductor also have the electron loss and the magnetic loss. But the parasitic electron loss is dominant for this kind of inductors, because the silicon the commercial silicon, the magnetic loss factors can be negligible. So this major consideration. Based on this kind of understanding, we form this kind of dual tank circuit to illustrate our concept. So here we have the first resonator, which actually are LC tanks, and we have a second LC tanks. We want to put this two resonator or LC tank as closer as possible to make them copying each other. Between these two resonator or LC tanks, you will have the magnetic coupling and also the electrical coupling. So this coupling coefficient can be defined by the EMF field of these equations. This Km defines the magnetic coupling efficiency, and the Ke defines the electric coupling coefficiency. And we put these two LC tank or resonator as close as possible, which will be equivalent to a equivalent resonator or equivalent LC tank. We do the analysis based on simplified second model. We do the analysis. The qualifier with respect of the A and B to LC tanks based on the K equal to 0.5 and K equal to 1. The qualifier is dramatically improves due to enhance of the magnetic coupling. That means most energy actually storage in the transformer due to the magnetic coupling. So we generalize this kind of dual tank to the multiple tank. We have this kind of second matrix. We can see this LC tank from LC tank 1 to LC tank N. This LC tank will be mutual coupling based on mathematical mutual coupling together. We can derive the matrix, coupling matrix based on the careful laws. We generate this kind of matrix. We dissolve this kind of, solve this kind of equations. We get the two resonant frequency based on the single port network analysis. We can see the first operation frequency, resonant frequency, is actually almost omega-1. It's related with the tank number n and also the LC tank values, the value, inductor value, and the capacitance value. And if k equal to 1, we can simplify the equation, become Q1 equal to this one. Based on this kind of equation, we can get this kind of insights. There were two frequencies. These two frequencies can be adjustable either by inductance value or capacitance value, and also the tank number, and also can be adjusted by the coupling coefficient k. And the second insight we can draw is can form two or multiple networks, and the qualifactors is related to the tank number n. So we do the analyze based on the circuits, and then we can see we can increase the tank number from 2 to n. Actually, the operant frequency as the first resonant frequency actually shift to the low frequency, and also that means if we shift to low frequency, that means the circuit size can be shrink, can be reduced. And the second thing we can see, with increase of tank number based on the coupling coefficient equal to 0.5, we can see the qualifactor is also dramatically enhanced. So the equivalence LC tank qualifactor actually enhanced. So based on this kind of advantages, apply the US patents, coupling multiple tank circuits based on the US patent. And here below, in the following parts, I will give the introduction of how we use this kind of multiple tank concept and the topologies into our circuit design. First of all, I will give some design examples used for the water control oscillator and also the frequency divider application. And both this kind of VCU and the frequency divider are the key building blocks in the accurate RF microwave source or synthesizer. And overall exist in all the RF microwave transceiver for smartphone or equipment. So let's see the examples. First of all, we apply this kind of concept into the VCU design. We design based on the triple tank concept for the VCU design. We can see when let's the K coupling coefficient K equal to 1, the qualifactor can be enhanced to 2 times compared to the fundamental LC tank. And if we based on the tree tank can be even further enhanced. So based on this kind of design, we can dramatically enhance the qualifactor. And due to the qualifactor enhancement, based on the listening equations, the phase noise of the VCU also improved significantly. And we also do the publication in IWFC conference based on these kind of ideas. And we also build this kind of circuits which can be seen the VCU have very, based on triple tank, have a very low power consumption, just the DC power about 9.8 milliwatts, and the output power up to minus 3.1 dB. And the frequency coverage have a very broad frequency coverage because we use a multiple tank. Each tank can be adjusted based on step by step and based on digital control. So we can broaden the frequency operation range as well. And here we also compare our design with the state of the art, we can see the frequency tuning range can be up to from the 23 gigahertz up to 26 gigahertz. And the figure merit we achieved up to 185 this kind of performance. So the overall advantage we achieve by using this kind of multiple tank technicals for the VCU design, we achieve the wide tuning range and a good phase noise and the best power added efficiency. That means the energy saving schemes by using this kind of topologies and also low power design. And we also use this kind of concept for the inject lock frequency divider design. So these are based on similar ideas, similar concepts. Use a multiple tank as resonators for the frequency inject divider. So we also broaden the frequency range to cover from 21.4 to 25.1 gigahertz. And output power we have at minus 2.5 dBm, and the DC power consumption is 5.8 dBm. And we also do investigation recently, as I think there's we also divide the dual tank injector frequency divider, which we do a good compromise between the phase noise, locking range, and the power efficiency, and also the chip error by using this kind of multiple tank. Because this kind of multiple tank, we can build based on the multiple mental layers. For example, we illustrate the 6 mental layers. We can follow use this system. The circuit size can be reduced by design use a 6 mental layer. We increase the actually vertical integration to reduce the surface areas of the total chip areas. And the circuit design becomes 3D design to shrink the size. This is a major trade-off. And we also use this kind of idea to build the dual tank, the triple tank wider tuning range voltage oscillator design, VCU design, which cover frequency from 55.7 to 66 gigahertz, which have very good performance, and the chip error is only 0.347 millimeter square. And you can see the size here is actually reduced. The total size is actually reduced. And the design concept is we use a dual core concept and a triple tank. And the first tank use a Gerber cell as a negative resistance for the oscillator. And the second core 2, and also this core 1 and core 2 are coupling together based on the magnetic coupling. And the third tank is which actually use a transistor together with the inductors to behave as a third tank. The third tank will collect the output power of first tank or second tank. And the operation will in this kind of manners. We have the first, during the first tank operation, the second tank will be off. And to save the power, during the second core off, the tank is still there to enhance the first core oscillator LC tanks. So by doing so, we let the first core to cover the low frequency band, and we'll let the second core to cover the high frequency band. By doing so, we can have a very broadened, double the frequency tuning range, while the phase noise enhanced, and also the tank color factor enhanced. This advantage can achieve by using this kind of tricky design, use a multiple tank. And here we show the design implementation and examples here. We use a dual core. We have a wide tuning range and a good phase noise, and no need buffer circuit, because as we know, when we do CMOS circuit design, the buffer circuit normally draw a lot of power. We use a transformer to replace the active buffer circuit to save the power. So the overall chip error reduced and the power also be reduced. And we also do investigation about this kind of multiple tank used by other research. Here's some examples from the other groups. We use they use this kind of probability for the circuit design. They also achieve very high frequency, 73.8 gigahertz, and the tuning range up to 41.1, and also have very good phase noise. And this is also based on the multiple tank set to finish the design. They are, based on their comments, they actually use a magnetic tuning much more and achieve ultra wide frequency tuning range. And this from other research group, Zhihua Wang's group, they also use this kind of multiple tank concept to design the VCU, which operate at 59.3 gigahertz tuning range, 38%, and the DC power consumption also very low, 8.9 to 10.4 milliwatts, and the chip area it actually is also reduced significantly. So from this kind of example, we can see the tuning range is a wideband without degrading the resonator's quality factor by using the even mode or odd mode tuning. And here's the other groups use this kind of multiple tank concept for the second harmonic impedance control to enhance phase noise performance and as well as in the frequency tuning range. Due to the time limitation, I will not give more detail about the design. But we can clearly see this kind of concept actually reduces the phase noise and enhance the performance. And here's some examples. You can see the chip area is also very small. And this some other design use this kind of multiple tank. Here is actually triple tank, triplet coupling tank from the Wei-Hong's groups. They designed the wide tuning range frequency control oscillator, which also have very good performance and design. And this from other groups for the class F type VCU design use multiple tank concept. And I think based on this investigation, we can see this kind of multiple tank technologies is now widely using the VCU design to achieve very good phase noise and also the performance. These other groups, Kaixue groups, we use a triple tank to enhance the circuit performance as well. And these are some other design for the terahertz VCU. The optimal frequency up to 239 gigahertz for very high frequency use a multiple tank concept to finish design. And this another example for the 150 gigahertz to 190 gigahertz VCU design. From this kind of thing, we can see now this kind of technologies become very popular for the RFIC design for high performance. And we also use this kind of multiple tank concept for the amplifier design, because RF millimeter amplifier is a key building block for in RF millimeter wave system design, especially for the transceiver and other type applications. Here we build some amplifiers use a multiple tank concept. We design the power amplifier, which based on the 65 nanometer CMOS process, which have the gain of 26.6 dB and outpower consumption outpower of 19.7 dBm. Use a CMOS process and very broad bandwidth. Here we show the performance. We can see from the design, we can see we have very broad bandwidth and also the very small chip errors, and the power efficiency is very good based on compared with the state of the art. And we also use this kind of concept to design the reconfigurable amplifier based on silicon germanium by CMOS process. Use a dual tank to fine tune the optimal frequency as well as the matching load. By doing so, we can achieve very good power adding efficiency of 55.9% of PAE. And the gain can be variable from 1.8 dB to 6 dB. And the frequency coverage can be from 24.3 GHz to 35 GHz by using this kind of multiple tank concept. And we also use this kind of concept for the low-loss switch design. Here we show some examples for the 60 transceiver design topologies. They use either you can choose dual antenna schemes, which might need a filter and antenna and a power amplifier as well. And also you can use a TDD scheme. That means you might need the SPDT and also the filter for the design. For our design, we proposed the SPDT filters. That means the switch behave also as a filter during the operation. So we do this kind of combined design. We do a comparison between the state ops. For the switch, the minimum loss based on investigation is about 3.5 dB at medium frequency band. And for the filter performance, here we have the table. The loss actually based on scheme. This second scheme, the traditional way second scheme, the overall loss, the filter plus switch, the loss is actually around 6.4 dB to 9.3 dB. But based on our proposed filter switch scheme, actually we can achieve the low incident loss about only 3.2 dB. Here we show the design example. We first of all use this kind of multiple tank to build the SPST single through switch. We can see the incident loss is only 1.8 dB, 9 dB. And they also use this kind of multiple tank to build the SPDT. We can see the incident loss only 3.2 dB. And the isolation at 60 Hz about 20 dB. And the switching on off time is very short. And it's only 0.18 nanometer. And the additional benefit we achieved actually the power handling, because we use a multiple tank. Each tank will separate the storing the energy. That is overall the power P1 dB and also increase of a number of the tank. So we will have very high P1 dB, more than 21 dBm, because due to the limitation of the test equipment cannot get the exact value. And the key feature we can achieve by using this kind of multiple tank for the filter switch design, we achieve the compact size, low incident loss, and high P1 dB and power handling capability. And we also use this kind of concept for the terahertz frequency IC design. Due to the time limitation, I will not go through the details, and just a brief shows the result. By this one, also you use an internal tank to control the coupling efficiency, coupling coefficiency, and to fine tune of the matching as well. Here's the analysis based on triple tank concept for the circuit design. We can see the small iron reflector short port 3 to the ground to stemming the power while enhance the polyfactor. And here we compare when the coupling coefficient change, how the operating frequency band got affected, and also the performance, the S21 as a transmission performance got affected. And we also form actually form a second order bandpass response. Here we'll also do the analysis based on the switch on or off conditions. And then here we do a comparison based on the scheme 1A and scheme B. And we have a very small chip error, just 0.035, and every size reduced by 90% of the circuits. And then here we show the merge performance for the 140 to 180 GHz. The incident loss only 3.3 dB, and also isolation can be enhanced by using this kind of auxiliary coupling lines. And here also we measure the return loss and also the switching time. The switching time is very short, within the second. And here also compare our design with the set us. We can see we saving the chip error by 90% for our design. And here's other design for the terahertz range. And we also use for the transceiver design by using this kind of multiple tank concept. We build this kind of dual chip transceiver, dual chip solutions for 6 GHz short range wireless communication. We built this transceiver chipset based on silicon germanium by CMOS process and the baseband chipset based on the 65 nanometer CMOS process. This 6 GHz transceiver SoC and this the demo board and the packaging and also temperature packaging with the antenna. It's actually AIP streams we build in these kind of systems. And here we show the based on this kind of transceiver chipset, we can support 4 gigabit per second based on EVM about 9.8 dBm per second. And we also show some demonstration. We can do a communication distance about 10 meters to do the video broadcasting from one end to the other end. And we also build the synthesize by using this kind of multiple tank concept, which have very good performance and a very small chip error as well. And for this kind of scheme, also used for the other building blocks, transceiver building block applications. And for future applications, this kind of multiple can form, using this kind of multiple tank schemes can form multiple port silicon system applications. And also can be used as a low loss matching networks for the circuit matching applications. And can be used for the high power combination scheme using multiple tank. And it can also be used for the energy harvesting applications and can be used for the other off-chip applications. So for this kind of multiple tanks, the key feature or key advantage we can achieve is a low loss, high Hall factors, and compact size. And below, I will show some our related work for our team. Because our team right now builds the RFIC design, which cover from 300 megahertz to terahertz frequency range. We do a lot of verification and research on the silicon CMOS, BiCMOS, and CMOS SOI silicon oxide CMOS process. And we also build a lot of IC for 3.5 gallium arsenide MMIC design. And we also start from IC to the whole package design to finish the whole design chain. And we also proposed new design scheme for 3D integrated platform, which calls the substrate integrated suspended line technologies for circuit design. We actually do a lot of research and a lot of publication based on this kind of seesaw platform. And right now, we also do a lot for the 5G millimeter wave application. Here, right now we finished some design of a 28 GHz transceiver for this kind of base stations, and we also build some phase array front end use a BiCMOS process for this kind of beamform 5G base stations. And we also do some innovation design for the dual band transceiver chipset, which have the dual mode operation, which we have the 28 GHz mode or 39 GHz mode. That means a single chip can support dual band operation. That means you will have an even better application for this kind of chipset. So this kind of dual chipset, we actually integrated the dual band LNA, ultra-band mixers, and also the synthesize, which become a fully integrated SoC for 5G applications. And here's the performance for the TX mode, the overall gain and the performance. And this for the receiver mode conditions, we can see we have very good gain and gain flatness. And also build some by use CMOS process, use some high resolution phase shifter design. And we can see we cover actually 30 to 36 gigahertz and very small chip error, but we have very good phase resolution and we can cover from 360 degrees, and with RMS very small. And here's a measurement result for the amplitude error smaller than 0.2 dB and the phase error smaller than 1.3 degrees. And we also built some a new FEM for the next generation Wi-Fi applications at the IWFC 8.11ax standards. And for these kind of applications, the major issue is how you design the very low noise and very high power efficiency. Especially you need a counter in the very high linearity, because we need for this kind of Wi-Fi 6, you need to support very high order modulation, 1024 QAM modulation, which have a very high linearity requirement than the Wi-Fi 5 or Wi-Fi 4. And here some example, we use a Generalized to build the power amplifier, and we also use a SOI process to build the LNA low loss amplifiers. And with this one, I will draw my conclusions. And the new methodologies of multiple tank topologies is proposed to elevate the substrate loss issue for commercial silicon. And the application in new circuit like VCU divider and amplifier switch are verified the advantage of the proposed method. The techniques are adopted in 6 transceiver SoC, and the other related work of our team on 5G millimeter wave and sub 6 GHz application also introduced. And we also support by our lab facility. We have a very good test equipment which can cover from 100 MHz to 140 GHz, 1.14 terahertz proper station system, and also the oscilloscopes and VNS, all these kind of facility will support our IC design and development. And with this one, I will end my presentation. Here's big pictures of my campus, the Tianjin University, which is the first modern university of China, located in Tianjin. And very nice pictures is the top picture is from our old campus, and the below is the new campus. We also have a lot of faculty position opening worldwide to get the good talent for the teaching and the research in Tianjin University. Welcome. Thank you.
Thank you so much, Professor Kaixue Ma. And of course, that was a really great presentation. And we've got some questions for you. So we're going to move straight on to the Q&A, starting with this one. Can you explain the pros and cons in the multiple tank techniques for IC design used in low frequency and high frequency? Would you be able to elaborate on that?
Okay. Because this kind of multiple tank, we can use for low frequency as examples shown in the presentation. For the low frequency, we can use a multiple layers to dramatically shrink the circuit size, because we know the circuit size is related with the wavelengths. Because at low frequencies, the wavelength is larger, and if we use a multiple tank, which can be vertically integrate the multiple tank to shrink the size of the overall chip areas, and also the tank, the quality factor also enhanced. But for the low frequency, I think there's a major, we have a lot of advantages. There's almost no disadvantages. Of course, maybe the disadvantage maybe is the design complex. We cannot, because the design will take a lot of time to make sure the design can fit your expectation. And for the millimeter wave frequency, because the circuit size becomes smaller, if you use a passive element, for example, inductor or tanks, the size is shrink. We cannot use a very high tank numbers. For example, we can use a 2 tank or 3 tank, but we cannot use a 5 tank due to the size too small to for the layouts, the trace routing. They will have the wavelength limitation for very high frequency. Yeah,
Thank you so much for that answer. We have another question. This time it's from Diana R. And Diana R says, what type of modulation have you used for transceiver design and how is it verified?
Okay, actually for our design, we do have several different types of RF transceiver design. For 60 GHz transceiver design, we actually merged the 60 QAM modulation scheme measurements, which can support actually 4 gigabits per second. And for the some power amplifier design, we actually use a 256 QAM modulation scheme to do the measurements. We actually use oscilloscopes to test the constellations and also the EVM to verify the linearity and the efficiency. And for our new recent research for the Wi-Fi 6 applications, we actually test based on IEEE standards, IEEE 80.11x standards, which were classified from MCS 0 to MCS 7. We based on standard to measure the performance, to test the linearity and the output power specification to make sure it fits the application. Thanks.
Thank you so much, Professor Ma. We have another question over here, this time from Brinda S. And the question is, how can deep learning techniques play an important role in beamforming? Please explain.
Okay. Actually, the beamforming is because we majorly use for the hardware design, but for the beamforming, I think there are several ways. There are 2 ways. Actually, there are 3 ways. First way is to use the analog beamforming, and the second way is the digital beamforming, and the third way is to combine the analog and the digital beamforming. Because for the system applications, especially for 5G or 6G application, we will have a lot of transceiver front end. So the power consumption and the size and the cost become major issues. So we need to do a good trade-off between the cost and the beamform, the element numbers. So for the artificial intelligence, it's very good technologies to use the beamform, because if we use it for the MIMO applications, we need automatically turn on or turn off certain channel or certain transceivers to save the power. And we also need to have very good coverage to make sure the user can be linked by using this kind of MIMO systems. So artificial, this kind of technologies will become a very good baseband solution to support this kind of beamforming, to have a better power efficiency and even better coverage and better user experience. Thanks.
Wonderful. Here's another question, Prof. What are your comments on the application of wave for 5G application, and why do you design the dual band transceiver for 5G wave?
Okay, because right now the 5G worldwide, they have a different frequency band. For example, we have a 28 gigahertz, 28 gigahertz, and 39 gigahertz. There's two frequency band. The right now solution is they have the 28 gigahertz transceiver as one chipset, and the 39 gigahertz transceiver as another chipset. And these 2 chipsets become a standalone chipset. Because if we use a single band transceiver, single band is the traditional ways, that means just a single transceiver can be only used one application scenarios. For example, 28 gigahertz transceiver can only use it for the 28 gigahertz application scenarios, and the 39 use it for the 39 gigahertz transceiver application scenarios. But for our proposed solutions, we can cover the dual band 28 gigahertz plus 39 gigahertz. So for this kind of chipset, we actually the chipset area not increased, but the chip can be used for two applications. For example, for 28, we use the same chipset, dual band chipset. For 39, we also use a dual band chipset. By doing so we have one chip have more application scenarios. That means you will have more user to use this kind of chipset. This is my design concept. Yeah.
Great. Thank you for sharing that with us. And the questions continue to come in. This next question is higher level QAM and OFDM need more RF backoff for linearity. How do you overcome this challenge to achieve good power efficiency for the power amplifier?
I think it's a very good question, because right now we move from 4G to 5G, even to 6G. What's the major issues we face is actually the bandwidth. We actually have a very broad bandwidth. This brings a lot of challenges for our circuit design. And then another challenges is band use efficiency. We use a high order modulation schemes, for example, 1024 modulation schemes. So for this kind of high order modulations, the system linearity requirements become very stringent. These are two challenges we faced for 5G and 6G applications. So normally for the power amplifier, of course, for the whole transceiver design, we all need to consider the linearity issues to do a good trade-off. The most dominant thing is about the power amplifier, the final stage of power amplifier. Normally, we need a bank of 6 dB, even 9 dB, even 12 dB to have even better linearity. That means we actually bank off the design, because actually the power amplifier itself have out power capability up to, for example, 33 dBm, but we actually use during the application, we only use at 23 dBm, which we bank off 10 dB. That means your power efficiency will drop. So this issue we faced. How we deal with these kind of challenges? We need to find the new design ways. For example, we can use the Doherty schemes, new Doherty schemes, either the dual pass or three pass, to increase bank off efficiency, while at the high power conditions, the power efficiency is still very good. This is a very good solution we needed to do. Of course, we have also have some new schemes. I use some new topologers to even have a better power and efficiency for bank off condition applications. I think in summary, I think we need to do a good trade-off to select the good topologies, new topologies, to have a good linearity. And also we need to have good bank off schemes, and also need to have some DPD scheme to increase the linearity while improve the linear out power. This is my answers. Thanks.
Thank you so much for that explanation. Our next question coming right up is this. What Wi-Fi IC and module do you build differently from the existing Wi-Fi?
I think I just brief. We do something right now ongoing. We just send for verification. I think we can have a better power efficiency and even under the bank off conditions, because right now the linearity we need to meet the standard requirement from MCS 0 to MCS 11. There are some standard requirement based on IEEE 802.11x. So we need to meet the standard for the linearity and also other specification. But we need new schemes. For example, we use some current reuse or some different topologies to saving the power and increase the PAE for our chipsets. I think I don't have the picture to show here. We just discuss based on some concept. This the way we're doing right now. Yeah.
Thank you so much, Professor Ma, for answering all those questions from our audience. And of course, a thank you to the audience for being so participative. We have 2 more speakers coming up later, so we look forward to more of your questions in the chat box and the Q&A tab as well. Once again, thank you, Professor Ma, for that in-depth look at generalized multiple tanks and applications for silicon-based RF MM wave IC. Thank you so much, Prof, for joining us from Tianjin.
Okay, thank you. Thank you.
Thank you so much. Now, this morning's presentations truly leave us with much to think about. And after a short break, we will be rethinking communication theory for wireless network systems. So do join us back here in about, I believe time right now is, we've just got a few more minutes for the break, 10 minutes, 10-minute break. We're going to be going for a 10-minute break, and we'll be back here at 11:15 a.m. We'll see you then.
Design is many things to different people. Most would associate it with art, fashion, and graphics. But that is only one facet of this multi-dimensional concept. Design, more importantly, is also the creation of human-centered solutions. They can be solutions to everyday challenges that make life easier, like adding wheels to your luggage to create the modern 4-wheel suitcase. Or they could be solutions to global challenges that affect the lives of millions, like the creation of a shared network where information can be exchanged at any time by anyone at any location, what we now call the Internet. Design is the sum of ideas and expertise from different Design is many things to different people. Most would associate it with art, fashion, and graphics. But that is only one facet of this multi-dimensional concept. Design, more importantly, is also the creation of human-centered solutions. They can be solutions to everyday challenges that make life easier, like adding wheels to your luggage to create the modern 4-wheel suitcase. Or they could be solutions to global challenges that affect the lives of millions, like the creation of a shared network where information can be exchanged at any time by anyone at any location, what we now call the Internet. Design is the sum of ideas and expertise from different fields to create an effective, efficient, and sustainable solution. Nurturing design innovators is crucial to the continued advancement of humankind in a world bombarded by unprecedented challenges. They will transform our lives, drive innovation, grow economies sustainably. And at Singapore University of Technology and Design, also known as SUTD, our mission is to nurture the future generation of design innovators. Inspired by the evolution of design thinking, SUTD is revolutionizing design and leading the charge towards a new era of innovation. Students, of which 40% are female, are trained in design innovation and are immersed in a collaborative learning environment where they can easily go from concept to prototype, programming and testing. An interdisciplinary curriculum brings together 5-degree programs for more holistic and creative innovations, be it in education or research. We are united and inspired by a single-minded goal of improving lives and safeguarding our planet. We call this a better world by design. From autonomous systems that can learn and adapt to new innovations in sustainable materials, design with the power of AI can help build smarter, more enjoyable cities, unlocking breakthroughs beyond our wildest imagination. It will also help power our economy to stay competitive into the future. Design powered by technology and AI truly is here to help us build a better world.
And welcome back. Hope you managed to recharge during the break. And now our next session will be Rethinking Communication Theory for Wireless Network Systems. Now, wireless network systems, or wireless networks rather, are evolving to cater to emerging cyber-physical and mission-critical interactive systems, such as swarm robotics, self-driving cars, and smart Internet of Things. Now, this talk describes some of the shifts in thinking that may be needed to develop a post-Shannon theory. And it will also highlight the potential as well as the challenges of goal-oriented communication, which aims at redefining timing, importance, and effectiveness in future networked intelligent systems. To help bring us through all of this is the Professor and Chair PI on Advanced Wireless Systems at the Communication Systems Department, Eurocom. He has received several career and best paper awards, including an ERC Consolidator Grant in 2020, the IEEE Communication Society CTTC Early Achievement Award in 2016, and the Outstanding EMEA or EMEA Young Researcher Award in 2013. Ladies and gentlemen, let us welcome Professor Marios Kountouris.
Good morning, everyone. Thank you very much for the introduction, and thank you very much for the invitation to this very stimulating event. Let me share my screen to start the talk. Okay. Can you see my screen? Is everything fine?
Yes, we can see it very clearly.
Okay. Thank you very much. So today we're going to talk about how new systems, 6G or even any future generation, could impact the way we design things and how to redefine our research tools and also our practice. So before starting, the first question, and I think many other speakers have addressed that, is what 6G will be. What's going to be, actually. And whenever we want to design a new generation, the first question would say, okay, it's going to be just a faster new generation. So like 6G could be a faster 5G. But then we always have the question, should we go for a clean slate approach? Maybe we should do something radical. Any new generation tries to do something completely new than the other ones. But then comes the question, okay, which are the key technologies? Which are the enablers for that? Do we have the right theory, the right techniques, the right algorithms to do that? And also, these days, there are many people saying that, okay, 6G is going to be probably something which have a lot of machine learning and AI inside. So maybe we should not care much about some physical layer design or some communication theory, because, you know, we're going to let some part to the data-driven approaches. And there have been always a bunch of discussions and papers saying, okay, is physical layer dead? Do we have to do something on wireless? Maybe some people say, okay, we're close to the fundamental limits, so there's nothing new to be done here. Maybe wireless theory will bring something just a small epsilon to the whole picture. So maybe we should focus more on the applications or to some system integration. And this is what we're trying to see in this talk. Are we really in that situation? So the first thing is, like, if somebody asked me to paint how future wireless communication will be, or how 6G is going to be, I think with a bit of exaggeration, the first picture that comes to mind is like the situation is something like this. There's a lot of people sharing their vision, and there are different technologies coming into play, but we don't have a clear answer what 6G is going to be. But of course, the situation is not that hopeless. So we'll try to design things the way we want, and then there's some kind of emerging consensus of what 6G we want to be. So 5G has had this kind of triangle, and having this requirements, the KPIs, the key performance indicators for not only for mobile broadband, the EMBB, but also brought some new exciting things about ultra reliability and low latency, and start thinking that, okay, broadband and high rate and high spectral efficiency is not the only thing that we have to care. There is a lot of connectivity issues. There's a lot of sensor-enabled machines that will come and will provide connectivity for, and this is what we want to care. Now, 6G is going to probably take some of these KPIs and bring it like with a factor of 10, 100, and go to some extreme requirements, but it's also is going to have a mixture and some kind of contours of these kind of things. So it's going to be more like a pyramid or a more complicated form where we want sometimes to have low latency, ultra high reliability, but also not for short packets, but also for long packets, for high throughput applications like the virtual reality things. We're going to have like peak rates of 1 terabps. This is what we're dreaming of, and the challenges are way bigger than what we have. Now, of course, as I said, things are not that desperate. We have a consensus view. The community research one and also the practitioners are contributing to that. And 6G, more or less, we know that it's going to be something that will provide virtual unlimited connectivity. So now connectivity will never be an issue. Everybody is expecting to have this. And having almost like zero failure. And everything is brought to the extreme, like ultra low latency, ultra high precision, very high peak rate, like terabps. And of course, we're going to talk about multi-service and multi-tenant networks. And there is also a consensus in the timeline. We have also the standardization activities with 3GPP. So things are, let's say, on track. And there have been a bunch of proposals about the technology enablers for that. And everything is basically going beyond. Like we're going to go beyond the MIMO and the massive MIMO and go with large intelligent surfaces or reflecting surfaces and meta surfaces. Probably we're going to challenge the notion of cell and go for cell-free architectures. And again, we have the typical debate of should we design a new waveform and go beyond OFDM, going to higher frequencies. These are things that, of course, expectedly come into the pictures. Of course, now, if we think it from an engineering point of view, what the future challenge is going to be the hardware. Now we start touching the limitations and the challenges that we're going to have from the hardware perspective, whether this is the ADC, the digital converter, and the electronics that might have some fundamental limitations. So maybe we do not have limitations in terms of, let's say, information and communication theory in certain parts, but we might have limitations from the hardware we're going to provide to do that. And of course, there's always a big question mark because many generations try, for example, to challenge OFDM, but maybe we're not ready to leave our amazing engineering and designs we have done so far and have been successful just to get an extra gain of something that we were not secure that is going to work in practice. So many of these things also have a bit of skepticism. For example, people working on extreme high frequencies, we start realizing, for example, the challenges that we have. And then, for example, millimeter wave has been one of the key new technologies for 5G and probably 5G plus. But in terms of implementation, we see also the challenges. What we also know, or let's say we agree from different perspectives, is that there's a bunch of new services, applications, and use cases that we would like to see, and that we would like that wireless networks providing the platform and the foundation for them. Whether this is like kind of multi-sensoring, virtual reality, some kind of sensing and 3D imaging, tactile internet, consumer robotics, all these things are we're dreaming of, and we want the wireless to do that, to enable that. What we also facing and seeing is that now wireless and 6G wireless is not alone. is coming together, and there's an intersection with the analytics and the machine learning. We should face that as well. And we have also the IoT, the Internet of Things, and all these billions of start getting smart devices that they will communicate the one with each other in an autonomous way sometimes. And there is a big intersection there. Now, trying to define a bit, or in a simplistic way, what 6G could be, and even future generations, is like we started by voice for 2G, then 4G brought the mobile internet, and then 5G for, let's say, some people is just like the wireless internet for things. Now, what 6G will be? Is the wireless for what? For whom we design this? And for that, we have to look on the emerging ecosystem that we have, the wireless ecosystem, and we see a kind of emerging cyber-physical and mission-critical interactive systems. This could be, for example, self-driving cars, smart Internet of Things in the Industry 4.0, swarm robotics. We have a bunch of machines that will want to communicate, and sometimes in an autonomous way. And this kind of application calls for reliable real-time communication, autonomous interactions, and some kind of automated decision-making on a timely manner. There will be a lot of multi-source fusion and multimodal information from different sensors. There will be a lot of computations that they're moving closer to the device. There's an emerging ecosystem here. And also thinking that for, let's say, 2G, 3G, and communication that have were human-centered, we knew more or less the fundamental limits. We knew, for example, our limitation to watch a video or an image or make a decision, because we're human beings and we have our own limitations. But then, what about the machines that they cooperate in a very kind of sub-millisecond manner? Do we know the fundamental limits? So there's an emerging area of wireless network systems. So it's going to be a myriad of interconnected devices, that these devices will start having a lot of advanced capabilities in terms of sensing, computation, processing, even machine learning. They could make their own decisions based on data-driven approaches. So for me, let's say, and for some other people, 6G will be the wireless for the intelligent machines, all these interconnected machines, which bring a lot of pressing demands. For example, think of self-driving cars collecting information from radar, video, LiDAR, and these kind of things. And they have to process all that at a very high speed. They have also to exchange information with other cars, for example, to do a collision avoidance or to detect a pedestrian. And all these cars will communicate in a shared medium. So the amount of information that we should exchange, process, and also the consensus that the cars should have for a certain maneuver should be done in a very, very timely manner, especially if the application is critical. For example, not crossing a pedestrian. Or let's say, take this picture from RoboCap, where robots are trying to play football together, and they exchange information, and they have to coordinate and make a collaborative decision. These are environments that's very challenging for communication. And then the question we want to address is that, do we know how to do it? Are we at the position to have the right theory, the right tools, and the right algorithms to do that? And of course, in an efficient and practical way. To answer this question, I will go back to the fundamentals. I will go where all these wireless revolutions started. And this is coming back from to Claude Shannon, who started actually the whole field, where the key was that information for him, it was basically related to uncertainty and surprise. And it was measured by the uncertainty that I have in a certain, when I receive a certain message. So I gain information when I observe something unexpected. And that was the first link with from let's say communication point of view between information and entropy. And we have these two famous theorems of Shannon when I want to compress a source, an information source, I know my fundamental limits. And when I want to communicate data, again, I know the channel capacity and the rate up to which I could send for error-free transmission. That was the starting of information theory and then communication theory. And basically, this is the theory behind our favorite today's application. And it's undebatably a success story. All these kind of applications today and the wireless is based on this fundamental theory, to the point that some people trying to apply it in many fields and brought this kind of bandwagon effect. So let's go now what this communication paradigm has been. Going back to the famous paper that started this back in 1948, we have three key things. The first one is that the fundamental problem that we're dealing with is basically I have some information on one point and I want to reproduce it exactly or approximately at the other side. And what occurs is to reliably transfer this information and ideally in its entirely. Now, the second thing is that, okay, this information should represent something. So there's a message that has a meaning and has some kind of probably value, but for us, this is not important, let's say. Okay, that was the kind of master stroke that simplified the problem in a meaningful way and brought all this successful design. And the third thing is something that we normally forget or take it for granted, is that the encoder and the decoder are centrally designed. So they have some common background as well. They have some common code book, for example. The message is coming from the same code book. So they have some kind of context and background in common to be able to communicate. It's not a completely agnostic, autonomous operation. And of course, this create some kind of lore that this is the theory of information quantity and not of content. So it's like kind of information content agnostic. And because that was a success there. Back there, the problem was the noise rather than what the signal carries. And that has been suitable for classical human-centric communication, and that has been successful, undebatably. Now, of course, back then already, in addition to this model, it has been identified that, okay, we don't just see random sequences of bits, or we cannot always ignore what these messages are bringing to the other side. There is a semantic problem, which is how precisely the symbols that I'm sending convey a certain meaning. And there is also the effectiveness problems. It's like I'm sending some information to the other side for some reason. How effectively this changes the behavior of the destination. This is what some people will call it like kind of pragmatic information. And that have been already from, let's say, the 50s there, okay? But now we start facing the limitation. We start facing to need to design systems that they need this kind of radical change from, let's say, a classical Shannon theory to something that we will call post-Shannon communication theory. And this involves a departure, a radical departure from just a quantitative, purely based on entropy approach to something that takes into account the context, the information content, and also some qualitative kind of elements. So the vision here is I need a theory, I need a new theory to enable the generation and the timely provision of information which is concisely represented. So I transmit only what is needed at the other side for a specific goal. And then it's effective. It managed to solve my problem and my application in the best manner. And then also has to be arrived to the right point of processing or computation. And the key to do that is something that in our community now is emerging, and we call it semantics or semantics of information. This has become a commonplace here. But semantics has been associated with other things. Normally, like semantic web, semantics is the meaning of the messages. But here, semantics is not the meaning of the messages. We use this term with its etymological significance, which is important. This comes from ancient Greek. Is like important. That's semantics. So semantics here is not the meaning, although it's not excluded, but is related to the significance to the importance and the usefulness of the message that's transmitted to the other side with respect to a certain communication goal. Why is that? Because the communication paradigm is also something where we're in a situation where communication is not an end in itself, but a means to achieve a specific goal. So I send my information. So let's say robots exchange information to do something, to do some kind of navigation, or self-driving cars are exchanging information, not as an end, but because they want, for example, to do collision avoidance, or because they want to arrive to certain cooperative behavior. So there is a goal that I have to achieve. And so in this case, I cannot just treat packets as something which I don't care what they carry and when they have to be delivered and to which node. This package has a certain content, and this content has certain utility and value. So then I have to take this into account, subject to the goal, of course. And this also changed the thing from something that I transmit. So in the traditional way, we don't care where the traffic is coming from. But here we need also to start from where the traffic or the information is generated. So the big goal here that we're trying to do, and this is what a new communication theory, post-channel communication theory should do, is this kind of goal-oriented unification of the whole communication process, starting from the information generation, its transmission, and its utilization. Okay, so in Shannon's communication model back in the 50s, basically, and this is the typical picture, communication has been just a pipe, which we just want to make it bigger and bigger. And somebody's giving me some exogenous traffic. I don't know from where it comes. Just need to represent it, to send it to the other side. And then my typical metrics is like maximize the throughput, minimize the delay, or have a very good bit error rate. And normally what I'm doing is a kind of non-causal signal deconstruction. So the goal-oriented model comes and change and challenge, or a bit augment this communication model and start already from the generation of the traffic. Now I can generate traffic in a way of an active sampling. So I go and generate the traffic when it's needed to serve my goal based on what the source or the process represent. I send only the information that is useful to achieve my goal or the requirements of my application. And this involves starting from filtering, pre-processing, to also care about when to transmit what. And now the metric that I want to optimize is basically to achieve my goal, and I want to maximize the semantic value, the effectiveness of the information I'm sending on the other side. And this problem comes challenging when I have to do real-time reconstruction. So here we're not in a case where I have I can allow long sequences. Here I might start to have to decode or start reconstructing the source in a real-time manner, which is a completely different problem. So the big question that comes into play is that what is semantics of information? Because there are many people talking about this, and of course we say it's the effectiveness, is the significance, or the usefulness of the information, but this is a high-level perception. So we need to define it, and that's one of the key challenges here. So we define the semantics of information to 3 levels. The first one is at the level of the data source and the process that we observe. And this is what I will call the microscopic level. And this is related, the semantics is related to the relative importance of the different outcomes of the events or the observation of the same probability. Now, if I go one step further, I have the mesoscopic level, which is in the level of link communication links. And this is related to the quantitative, but also qualitative information attributes, which I will talk about a bit later. And there is a bigger picture, the macroscopic level, which has to do with some kind of system-wide information flow. And then it has to do with this kind of system state and timing dilation, which I will talk a bit later. So in the macroscopic level, as I said, it has to do with the relative importance of an observation. So for example, if you have 2 highly improbable events, So they arrive with probability very, very low, which means that the information I will get from this is high. If we neglect the context or the importance that each observer will give, from an entropic point of view, they are the same. If, for example, they have the same probability to happen, then they're the same. But from an observer's point of view, for a specific goal, they might have a different kind of value. Let's take the example, for example, that it's going to have a heavy rain or a kind of hurricane in Sahara Desert or next to your place. Let's say these two events are highly improbable. Now, the value of learning this from the observer point of view could be different, because although they bring the same amount of information from an entropy point of view, for the Sahara Desert, maybe you say, okay, it's good to know, but if it's next to my place, probably you're going to run your place and then try to protect something or your car or something. So there is a different value depending on who receives that information and for which goal. And in the simplest form, this can be expressed with some kind of weighted information measure, taking into account the semantics in this kind of space-time dependent functions that could skew, let's say, the amount of information a certain event carries. And there's a very intriguing connections with Renyi entropy and Renyi order, and it has very nice connections with the compressibility, the complexity of a signal, and so on. I will not go into the details. I will pass to the mesoscopic level, which has to do with taking into account different attributes of information. And information has two kinds of attributes. The first one is the inherent ones, the innate ones. And this could be freshness, precision, accuracy, for example. And it has also contextual ones that depends on the use of information that I'm doing in a specific time. And this has to do with the completeness of information, if I have to take a decision, the timeless, when a certain information arrive at the destination, it did arrive at the right time, it arrived late, and it's too late, it's arrived very early, and then this information is becoming outdated. All these things play a role here, and this is key for defining the semantics of information. So let's say an operational definition of the semantics of information could be that it's a function of this qualitative, innate, which is objective, and contextual, which has some kind of subjectivity, attributes of information. And of course, there's a very interesting duality in terms of the value of information. For example, we can have a measurement that have a certain resolution, and this resolution will always be there. And for example, we represent with an amount of accuracy the reality. But this precision could be very useful for a simple application. For example, if I measure the temperature in the room and I just need to know that it's, I don't know, between 25 and 27 Celsius degree, but this measurement can be completely useless if what I care is to find to measure the temperature in a nuclear plant. So information could have also its own value per se, but is also the value change depending on the context. And a definition could be that the semantics of information is just this a non-linear multidimensional, let's say, function of these attributes. Let's take a simple example to understand a bit better what we're talking about here. So for example, I can have two, let's say, innate attributes. The one is the freshness of information, which some people would be familiar as the age of information, which is the amount of time that has passed from when I receive a certain sample, at time t, and when the sample has been generated. Not when it has been sent, but when it has been generated. For example, here is not delay that plays into role, because maybe it's not only the transmission delay here, but it's also when this information has been generated. Think, for example, about news. Even if you receive very fast news that they are from yesterday, they are not that fresh as news that they arrive maybe with a bit more delayed from the physical layer, but they have been just sampled 1 second or 2 seconds before. They represent the reality more accurately. So this is, in a way, the freshness of information. Of course, there's a whole field behind and a lot of work on this. And I have a certain distortion between the signals. I have a signal X at one side, I reproduce it on the other side, and I have this kind of distortion. And I take a function psi here, which is just the product. So I assume that my metric here is a product between the freshness of information and the distortion. And of course, I have a contextual attribute, which is the timeliness, which can have, for example, this kind of representation. So I'm having the same value if I receive the information within this interval, but then if I exceed a certain time, then it has exponentially decreasing value for me. So I should receive it up to here, and then it's exponentially decreasing, and basically up to a certain point, it becomes useless. Now, I'm coming to the third level, which is this macroscopic one. And this is one of the most interesting ones, and let's say novel. Now, take here an example where, what is the fundamental problem here? The fundamental problem here is I have information generated at a certain time t in certain point in space, let's say A1 with this kind of coordinates, and I want to send and reproduce this information. I want to transfer this information to another point, A2, where it has different coordinate in space and a different time. And I have an observer, think of an observer, a robot, like taking measurements of the real world and the physical world. And I have the virtual world. I have to do some kind of remote monitoring at at A2. So this is the observer. And it gets a reconstruction of the signal. So taking the fundamental limits that I have to compress this information and the duration that I have, what we're trying to do basically is to minimize this kind of system level distortion that I will have between the two states, between the physical world state and the virtual state. And I have to basically synchronize these two images, let's say, these two systems. And I have to minimize the time mismatch and the asynchronicity that I will have. So this brings the analogy with the twin paradox from relativity, when basically times evolves in a different way in the two sides. And I have this kind of correction that I have to do for the dilation. And of course, I have to do it also for the evolution and of the state between the two ends. So this brings some kind of nice analogies with relativity. And of course, it's not relativity theory, but it has to capitalize on the analogies that I have, redefining time, synchronicity, and simultaneity in communication systems. And I can explore the framework that I have in mathematical physics and all this Minkowski space to be able to synchronize and have, let's say, two pictures very representative, the one to the other. Of course, this has a lot of theory behind that. Now, we wanted to go this kind of goal-oriented communication. Let's try to go a bit deeper and say, okay, how does the model looks like, and how does this change from the current approach? The model changed because it starts already with the information generation. So I have a certain process. It could be continuous time or discrete time, and it can be a general. And I take samples of this process when is needed, or when I have to, when there is change in the status or in the process, and this is what triggers a certain sample. But this has to be done jointly with whether I should be able to send to communicate the sample and reconstruct it given certain constraints that I have from the application. And of course, I will have from the reconstruction, I have a certain kind of metric. And normally how this can be some kind of real-time reconstruction error. I have a certain distortion, and this changes the whole design. And the key here, and this approach is not separable. The way I generate, the way I sample, the way I transmit information, the way I reconstruct it, given certain constraints for achieving my goal, it has to be done jointly. This is not the typical separability here that we normally use, at least for point-to-point links, that simplifies the problem. And it changed the way I have to do encoding. It changed the way I do reconstruction. It changed the way I generate my traffic. Of course, this is a simple problem. The problem is a bit more tricky when I have multiple sources, let's think it like multiple sensors seeing probably the same event. So I have here some kind of the same physical phenomenon seen from different sensors, from different angles. Think, for example, camera spotting at the same area, but seeing different kind of views. And this has to be, it has some correlation. I could exploit the sparsity here when I have to do the joint reconstruction or fusion of this information. And thinking this when it has to be sent over a shared medium, over a shared communication channel, things scale in a way that I have to change the way I solve the problem and in a meaningful way. And of course, the bigger picture as well is that this there's a multi-point communication here when I have a shared multiple access, and the idea is to take into account the goal-oriented design, but also take into account the semantic properties of the source and the application requirements to do my work. There's a lot of operation that have to be enabled here, starting from filtering and censoring what is the useful information for my goal. And then I have to do sometimes some kind of pre-processing, exploiting the sparsity, do some kind of feature representation, feature extraction, and send only the meaningful information to the other side. I could do some kind of pre-processing. Then, of course, when I have to reproduce, I will have to reproduce it probably not exactly accurate, but according to the accuracy that my application imposed to me. So this will open some kind of fast partial and approximate representation. And of course, there has to be a kind of network orchestration here so that we share the medium in the most efficient way. Let's go to something that comes naturally here. And this comes from rate distortion theory, where basically I have a certain source that I have to find the minimum rate I could communicate that source to the other side to over a noisy channel, so that I will get it with certain distortion. This is a well-studied problem, rate distortion theory, and this is basically where this is where I formulate this problem: the minimum mutual information subject to a certain average distortion constraint, and I get this kind of curves. Now, if you take this example, you'll see above something that has good quality, let's say, as compared to down. But then if you check it above, actually, according to my metrics, I will have a high distortion. But then the perceptual quality, it will have been better if I want, for example, to detect that there's a bidding here as compared to here. And below I have low distortion, but I have a bad perceptual quality. And this is an example coming from a paper from 2018, which shows that something that I measure based on distortion or the signal to noise ratio does not necessarily translate naturally to the quality as a user that I will see to do a certain goal. For example, detect the pedestrian here, or the something like a sign, or a bicycle. And this brings the notion of the semantic quality indicator that has to be incorporated into this rate distortion theory. And of course, this becomes challenging when I have to do with real-time constraints, when I go beyond the typical long sequences that our usual theory has. So here, if I put the real-time constraints, things change completely. And what I care is not only to minimize the distortion between a certain sequence or certain image has been sent at a given time, but I want also to minimize the distortion in a way, the distance between the statistics of the source. And this can be captured with a certain function, and this changes completely the rate distortion perception region, and it goes I need high rate to get a certain perceptual quality, a certain semantic perceptual quality, but then Do we have the schemes to achieve that? Is this achievable? Can we communicate in this kind of rate? Of course, how I will take the semantic quality indicator, a very simple idea. It could be a certain divergence between the probability distributions, and then what was a standing distance, for example, is one of a good ideas here. There's a lot of theory coming here, and this is a very interesting framework because it brings the bigger picture. And this, I think, is the last kind of new element I will bring. What is the bigger picture here, actually, in the semantics? I start with a very complex idea. I have something, a source that now is not just a 0, 1, a binary source that represents certain thing, but it have a certain semantically complex content that normally lies in a very high dimensional distribution. So I need to communicate a source that belongs to a certain high dimensional distribution. Now, I don't know how to do that normally. This is not something that I'm used to do that. Normally, I will have to do some kind of projection in a different information manifold, and I have a low dimensional distribution, something that I know how to transmit. For example, we know how to transmit Gaussian sources in communication. Then probably I will have to bring the problem down to what I need, so that I use some of my favorite tools. And the key here is that the encoding and the sensing and the preprocessing are all part of the same and bigger picture of the encoder that we have in Shannon theory. This will pass from a certain channel, so we'll get some kind of noisy distribution. And then I will have to decode, fuse, if it's like kind of multi-source information, reconstruct my source. But there is an intrinsic connection here with generative models, because at the end, what I will have to do is I will have to reproduce this semantic content, this complex data. And so for that, I will need to have a generative model for the distribution, which is normally high dimensional. I might not even know it, or even I might not be able to calculate the mutual information to do an efficient way of information transmission. And the bigger picture is basically I have to represent, to send a complex content or idea from one side to the other, and this change the whole way that I have to do communication. Either I will have to go for communication of high dimensional multimodal information sources. Is this the right way to just explore the complexity of my problem, or should I do the connections between generative models and optimal transport theory here, so then I can be able to reproduce with high fidelity the semantic data that I want to transmit on the other side for a specific goal. Of course, fidelity and timing here would depend on the context, and there is a lot of exciting trade-offs here, since sensing, preprocessing, coding, all these things come inside of the transmitter side, and then the reconstruction, the fusion comes on the receiver side, and this goes integrated, and we cannot only separate it. I'll do communication and somebody else will do the computation. And imagine that this is a point-to-point link. Imagine this being on a shared medium and having the distributed part of this. So does this work? We try these kind of ideas on a simple framework, and this has been on real-time tracking. And we have a very simple scenario when I have a robot that monitors a two-state discrete Markov source and is sending sample to the other side to do some kind of actuation. And then basically what I'm doing a real-time tracking of a simple source. And I have two metrics. The one is the real-time reconstruction error, which is whenever I have state, let's say 0 here, and I have state 1 erroneously at the other side, so I would reproduce something which is not correct, then I declare that I have a real-time reconstruction error, which can be also time averaged. And I have a certain of penalty or certain cost of the actuation error, because at the end is not, what I want is not to minimize the distortion between xt and x hat t. Is I have, let's say, robot that hits left or right with a certain hammer. What I care is whether I miss some of these events. And this penalty that we have can be also non-commutative. So, for example, detecting being in 0 when my original source is at 1 might have a different cost when, on the other when the source is at state 1 and I'm on state 0. Think, for example, traffic light. Sometimes it's better to brake if you detect erroneously that the traffic light is red but is green. You will embed traffic, but nobody's life is going to be in danger. But if you take a red traffic light for green and you accelerate, probably this might have an accident. So you see that the penalty or the cost that they have in the actuation error is not always commutative. And then we find we apply 4 different goal-oriented sampling communication techniques: the usual uniform and based on information freshness, the H, and 2 emerging ones, the change aware. When I generate a sample at the transmitter, whenever I detect a change in the state of the source, and go one step further and including also the receiver side, then I generate a sample whenever the transmitter and receiver have a discrepancy in the states of their signals, or the status basically. And this is what I get in terms of real-time reconstruction error and cost of actuation. So you see that for certain rapidly varying source and different probability of success, 0509, the semantics aware sampling and communication gets a real-time reconstruction which is very low compared to the traditional approaches, and the cost of actuation error is also very low. And all that comes, and this is the key, is that because I send the right information that I need so that I minimize my real-time reconstruction error and the cost of actuation error, and I don't send samples that are, let's say, useless or uninformative. And this is actually, these curves are obtained for the semantics aware and the change aware by sending less than 5%, sometimes even 1% or even lower of uninformative samples, where in the uniform, for example, I will send samples that probably I could have avoided saying them because it's just like they don't bring anything into the problem and they just use resources, let's say, more or less for nothing. So to conclude, I will say that if we want to support all these autonomous real-time connected intelligence systems, these wireless network systems, we will need definitely a new communication theory and change or challenge certain of the prevailing communication paradigms that we have. And I presented a certain vision, a certain communication paradigm whose challenge is basically this goal-oriented unification, starting from the data generation and processing, the information transmission, and the reconstruction. What we expect to gain from that, basically, we will do a more, we'll have a reduction on the significant reduction in the amount of energy that we consume to sample something, to send something, and also the resources we're going to use, the congestion we're going to bring into the network by sending packets that they are not meaningful for the end goal that I want to achieve. And this also will improve the computation efficiency, which all of these are key for the scalability of this kind of autonomous real-time system. And of course, it will open many exciting applications. This is the foundation technology for a plethora of socially useful services, from swarm robotics, telehealth, environmental monitoring, and so on. This is some kind of new paradigm, and for that, I would like to also give the credit to the sponsor. This is also coming from the ERC Consolidator grant that I have been awarded, and I have to acknowledge the support. And if you want certain details or exchange ideas on this emerging topic, which is very interesting, you can drop me an email. And with that, I will conclude my talk, and I will thank you for your attendance, and I'm open to answer questions.
Thank you so much, Professor Marius Kountouris. And of course, we're going to go straight into some of the Q&As from our audience right now, starting with this question from PG Patil. And the question is, will there be a challenge from a data integrity perspective? If not, how do we validate to demonstrate data integrity? Now, the background of this question is regarding monitoring and communication of fast-changing process parameters. So, Professor, what do you think?
Yeah, thank you for your question. Very, very good questions. And There's a lot of things here about data integrity. There's also the security aspects here. Here, the idea is not to there's a misconception that we have to ask and I have to act on getting to know the data of a certain user so that I'm able to optimize the system. Here, the idea is that the user, which is now probably is a robot, will get some guidelines on what is the application that it has to support and how it needs to generate the data and transmit it to the other side. So it's not collecting, it's not having a central controller who is going to collect all this information, filter, so act on the data, filter them, and then do these things, get rid of some redundancy if it's not needed, and then send it on the other side. It's a different approach. It's like the node, which could be a robot, it could be a car, and so on, becomes the king of the process, and it has kind of autonomous capabilities to decide on the data. But of course, certain security aspects or data integrity have to be studied. And I didn't talk about security, but this is a very important topic here, definitely. About the real-time parameter things, yeah, real-time is actually one of the key things that makes things not trivial here. So that's the thing. We bring the communication theory into new constraints, which is the real time. And I don't work anymore in these ergodic long sequences, but it's this kind of, I have to do some kind of remote monitoring, remote estimation, remote real-time tracking with real-time constraints.
Thank you so much, Professor Kountouris, for answering that question. And we have another question for you. And this time, this question is goal-oriented communication a 6G enabling technology or not? What's your take?
So that's a good question. I would not call it a 6G per se, in the sense that this brings these goal-oriented things brings a new communication paradigms that it's a bit, I think, is a change in the philosophy and the way we design systems. That of course some of these ideas could penetrate or could feed the design of 6G systems. But it's a little bit bigger than that. So it will probably serve into the 6G plus, if we can already talk about the future generation beyond 6G. So it's not necessarily something that it will serve 6G per se, although it will inspire the designs. Of course, the faster we go, having a very meaningful theory that brings insights and useful designs, the faster we'll go to the 6D design and the standardization process. But it's also have very good interactions with other fields having to do with computer vision, control systems, and other activities rather than just 6D broadband.
Thank you so much, and we hope that answered that question. Our next question is this. The presented communication paradigm has similarities or can be seen as an extension of known concepts such as age of information and joint source channel coding. So how is it different?
Yeah, that's a usual kind of criticism or the first feeling of some people when they listen of this kind of new ideas. And age of information has been inspiring into giving certain ideas. So, for example, detecting that, for example, throughput and delay, they are not the right metrics all the time, or we have to do some kind of joint sampling of communication. They came from the age of information kind of work and community. So for some people, it's just a small extension of age of information could work. But here, this goes, let's say, way bigger, and just age of information is just one dimension out of, let's say, 10. So although it gives the insights, it's not just a simple, trivial, non-linear extension of age of information. There's a lot of other things that come into play. And although it resembles, especially the rate distortion theoretic framework, that in joint source channel coding, that is something well studied, here we have real-time constraints. So these are things that it hasn't been studied, or we don't have need solutions for that in the existing joint source channel coding theory, and or we don't always have the separability the way I have it, especially when I have to do content which has to do like image and video and not just a simple source. And of course, it builds upon joint source channel coding, but we're in a different area, and it's actually the problems that we have to tackle are way more challenging, and there's a lot of work to do for that.
Thank you so much. Now we have another question here. This time is about technical risk and challenges, and it's this. What are the major technical risks and challenges of goal-oriented communication theory? Can you explain?
Yeah, actually, as this is a new thing, and this is kind of an emerging topic, so there's plenty of recent challenges from theoretical point of view and practical point of view. But I think the key is first the theoretical point of view, which is also our focus here. I think the number one challenge is to define the fundamentals of the semantics of information, find the right metrics that will allow us to do things. So it's not going to just drop things inside, drop dimensions, increase the dimensions, have a big optimization problem, joint optimization problem, then it's hopeless to solve it, or I don't get any insight, and this kind of thing. The idea is to find the same way that classical information theory break down to entropic measures that was key to unlock the potential of the communication systems, is to find the right concise and tractable metrics that will allow us to do things, and also define concretely and in a mathematical way what is the semantics of information. Because as I said, this vision is also kind of shared from many people, and has been also articulated back in the 50s actually. Okay, yeah, I want to do goal oriented and take into account the importance, the relevance, the priority, and these kind of things. There's different flavors here, even in a working community. But what this concretely means, and how do I solve problems in a formal way, in a mathematical way, and in a theoretical way based on that.
Great. We've got more questions coming in from our audience right now. This next one is from Diana R. And the question is, how do you structure the project based on semantic communication? How do you do that?
Can you specify a bit more the question? When you mean the structure of the project, you mean the how the semantics will play a role here in the communication, or we refer to the project of like the ERC or something? Can the person give more? Yeah.
Let's see if Diana has an answer for that. Diana, if you can hear the prof, would you be able to expand on your question a little bit? Okay, maybe we'll come back to that later. We'll see if there's an expansion of the question. We'll go to the next question, and this one is from William Lau, and the question is, this post-Shannon comms theory seems to include knowledge of the application layer into the objective function of the comms. Today, with this new theory, the application layer will raise the QoS needed, and this will then change the comms protocols to deliver the service. How will this new goal-oriented theory bring value to this conventional way of doing it? It's a very, very interesting question.
That's a very good question, because that's also one of the challenges as well. How do I know the application goals, and what is the right information to send when I have to optimize this? So certain things it has by applying this sampling, for example, is by going to the application queues and apply my let's say filtering and censoring then already when I generate traffic. But certain of these things are transparent to the other, let's say, layers of the protocol, like layer 3 and 4, for example. Most of these things are transparent, so I don't have to, let's say, circulate all this information from all the way from the application layer down to the physical layer. And also, a companion question that is like, there have been also in the networking approaches similar to in spirit, like intent-based networking. I try to define my business goal, my business intent, and then I take this to account, optimize in a machine learning way. So in a way, here is going one step further and throw these elements, throw these guidelines all the way down to the lower layers of communication, like physical layer and media, MAC layer. So that's the thing. Now, how I send the right information without having to pass the optimization from all the layers and even cut some of these layers or being transparent to this layer is key. Otherwise, of course, I will lose the scalability. So there's a lot of thinking here, and there's a lot of factoring in the metadata that we'll need to process for that. So that's a very good question. And this is the next challenge, I will say, after the theoretical one, is how in practice you will have to do the signaling thing without killing yourself, basically.
Thank you so much, Professor. Let's take a look and see if there's any final questions or any expansion of the last question coming in. I believe there might be another question coming right up. And this was the previous question on semantics that is going to be slightly expanded. Hopefully this will be a little bit clearer. And here's the question coming on screen right now. Okay, so the question was from Deanna R. How do you structure the project based on semantic communication to apply semantic communication for the IoT-based agriculture application?
Okay, that's thank you for the clarification. So what's going to happen is that, okay, for whatever application you have, for example, agriculture, probably there maybe some of the constraint will not be real time, but could be taking into account the environmental, certain changes in the environment and so on. So for me, it will be, for me, this is communication theory. So it will be nodes with their own kind of capabilities. So if it's agriculture, maybe they are not mobile all the time, unless there's a robot moving here and there. They will have their own constraints. They will have their own science. And then what I will have to achieve. Let's say that the goal is to a simple thing. I will water my my plants or my trees when I detect that the temperature has been like that, the humidity has been like this, and so on. Very simple problem. No real time, of course, but maybe I will have to do it from an energy perspective. So I will have to detect the humidity in the resolution that I will need to allow me to do that. I will have to communicate among nodes to exchange information. For example, if the humidity is different when I'm very far from my from the field or in the center of the field, and so on. And jointly, they will have to exchange few packets, the right ones, which I have, of course, to define which are the key information attributes that I need here, so that at the end, in a very efficient way, in terms of resources, energy, and so on, these packets arrive to the decision we should water now for this amount of time, and so on. Could be also learning here. It's a learning process based on what I did yesterday, on the day before, what have been the past, past data as well that can be integrated. Now, how exactly to do it so that it doesn't get complicated? This is the challenge of this project, actually, and there's a lot of work to do. It's just starting.
Thank you so much, Professor Kountouris, for answering all those questions from our audience. That was truly a very, very eye-opening session indeed. And of course, thank you for the keynote as well on rethinking communication theory for wireless network systems. Thank you so much, Professor.
Thank you very much. Thank you for all the nice questions as well.
Thank you. And of course, we're now going to go for our final keynote for our event, and this will focus on random access for machine-to-machine communications, connection-based or connection-free. Now, with the new wave of digital revolution, wireless communication networks are experiencing a radical paradigm shift from the conventional human-to-human communications to machine-to-machine communications. To facilitate the massive access of machine-type devices, random access is expected to play a crucial role in the next generation M2M communications. This talk will also highlight the practical implications of the analysis to the access design of M2M communications. And to tell us more, I'd like to introduce our final speaker for today. She's a professor at the Department of Electrical Engineering of City University of Hong Kong. She has broad interests in communications and networking theory with special interests in wireless communications. She was a co-recipient of the Best Paper Award at the IEEE WCNC 2007 and the IEEE Marconi Prize Paper Award in 2009. She also received the President's Award of City University of Hong Kong in 2017. Ladies and gentlemen, let's welcome Professor Lin Dai.
Thank you for the nice introduction, and thank you for inviting me. Let me share my screen first. Let's see. Okay. Hello, everyone. I'm Lin Dai from City University of Hong Kong. My great pleasure to share with you about my latest research on machine-to-machine communications. I guess one of the great benefits of being the last speaker is a very well-educated audience. So we have heard machine-to-machine communications for a couple of times in previous talks. We know it's important. It's going to play a crucial role in our future communication networks. And here in this talk, we are going to take a closer look at its basic concepts and the challenges it brings to our communication network designers. And we would focus on the multiple access level, more specifically random access. So this is a field of long history with almost half a century. It has been widely adopted to many different communication systems with numerous protocols developed. But in stark contrast to its successful applications, its theory has been long behind. And in this talk, we're going to see why it's so challenging to develop a good theory for random access despite all the simplicity in concept. And we would also specifically focus on the two basic types of random access, connection-based and connection-free, and see which one better suits the machine-to-machine communications. All right, so this is what we are going to talk about in this talk. I'm going to start from the basic concepts of random access, machine-to-machine communications, why they are important, and how to establish a unified theory for random access. And based on the theory, how we characterize the maximum effective throughput for connection-based random access and connection-free random access. And eventually, I'm going to conclude the talk by highlighting the implications of the analysis to machine-to-machine communications. All right, now we start from the background. No doubt, we are experiencing a new wave of digital revolution. And one of the key driving forces is this vast array of machine-type devices. So here, machine-type devices refer to those automated devices without human intervention, such as sensors. And nowadays, billions of sensors have been installed in our homes, cars, business, city infrastructure. So it is predicted that by 2025, the number of machine-type devices is going to be 10 times of our human population. And that is why 2 out of 3 services for 5G networks are devoted for machine-to-machine communications. That's massive machine-type communications and ultra-reliable low latency communications, which you have been hearing a lot in the previous talks. So we have every reason to believe that this machine-to-machine communications is going to play an increasingly dominant role in our future communication networks. And to better understand this fundamental paradigm shift from our traditional human-to-human communications to machine-to-machine communications, let's see, first of all, how they are different from each other. Well, for traditional human-to-human communications, we use our handheld devices to browse the internet, share pictures, watch videos. So the services are usually bandwidth hungry. But usually we have a small number of users that are simultaneously served. And on the contrary, for machine-to-machine communications, the density of the machine-type devices could be order of magnitude higher. 5G networks, for example, are supposed to support up to 1 million devices per square kilometer. But the good news is that without human intervention, the sensors are usually designed for specific purposes, for example, monitoring the environment, the electricity, the gas, so they do not have a lot of data to transmit. And now, a big question is, with all these unique features of machine-to-machine communications, how to provide pervasive and efficient access for those machine-type devices based on networks that were originally designed for human-to-human communications. Well, to answer that question, we need to start from a more fundamental problem of all communication networks. That is, if you are not the only user in the system and you have to share resources with others, then how to share? This is what we call multiple access. Well, basically, there are two ways to do it. If you have a central controller to collect information from the network, then it can allocate resources to users. But if such a central controller is absent, then every user has to determine when and how to access in a distributed manner. And we call it random access. So this centralized access has been long adopted in several networks, meaning for data transmissions. But usually it requires a lot of signaling to coordinate users' transmissions. And that would cause a significant system overhead when the number of users is large. And resolving the resources, on the other hand, would lead to a huge waste of resources if users only transmit sporadically. And that is why for machine-to-machine communications, the access has to be distributed. Well, random access has been widely used in current communication networks. For example, in our cellular networks, this is what we do. The users with data to transmit would first send requests to the base station to initiate a connection. Just for example, in this forum, if you have questions to ask, then you can raise hand first and indicate the host. And then the host or the base station would allocate the resources after successfully receiving a request to the user for data transmission. So this is a typical frame structure for cellular networks, like 4G or 5G. And users would send requests in this PRACH slots or subframes, and all other subframes are reserved for data transmissions. And another representative wireless network is Wi-Fi network. It has two access mechanisms. For RTS-CTS access mechanism is quite similar to the MAC of cellular systems. So here again, users have to send a request first before they transmit the data packets. And in another access mechanism, basic access is different. Right? So every user would independently send their data packets. So it's like if you want to ask a question, you just unmute yourself and raise the question without getting consent from the host. So here, the common feature of this RTS-CTS access of Wi-Fi and the MAC of cellular networks is that the users would always send a request first before their data transmission. So that means here the data packets, they do not contain because before they are transmitted, a connection with the base station is already established. And we call it connection-based random access. And on the other hand, for this basic access of Wi-Fi networks, we can see that every data packet has to contend with others. And if they are failed here, then the time wasted in the failed transmission will be determined by the data packet length, which would be usually would be much larger than the length of a request. But the benefit is that here the overhead is much smaller compared to the connection-based random access because you don't have to establish a connection first. All right, so we can see here there are two basic types of random access, connection-based and connection-free. Well, to determine which one is better, we have to evaluate whether it is worthwhile to establish a connection. It's like if you want to eat outside and to decide whether to make a reservation first. Well, if it's a fast food restaurant, then probably just go. But if it's a fancy high-class restaurant, well, people would spend 2 hours eating and talking, then you'd better make a phone call first, because otherwise you may end up waiting for the whole night. So here, similarly, if you have a lot of data to transmit, then you'd better establish a connection first, because the benefit of this reducing the transmission failure time would probably outweigh the cost of system overhead. So intuitively, we have this critical threshold of the data packet transmission time, only above which establishing a connection would be beneficial. And once we have this critical threshold, we can address a lot of important issues. For example, for Wi-Fi networks, when should we activate this connection-based RTS-CTS access? And currently, we barely use it. Is that a right thing to do? And for 5G networks, its connection-based random access procedure has been long criticized for its low efficiency. And many people have been advocating to replace it by a connection-free one. Is that a legitimate concern? And ultimately, for future networks, should we use this connection-based random access or connection-free random access? And to answer that question, we first have to know how to characterize this critical threshold, and that requires a unified theory of random access. So here we take a closer look at some basic concepts of random access. We know that for random access, each node has to determine independently when and how to access. So for each node, it has to answer 3 questions, very simple questions: when to start, when to end, and what if the transmission fails? Well, the first question, when to start, simple. You just transmit when you have data packets. And that's indeed our first random access protocol, Aloha. But despite its simplicity, it may not be efficient because the ongoing transmissions may be frequently interrupted by the other transmissions. So a more polite solution is to sense first. So transmit only when you sense the channel idle. And that is called CSMA. But here, the basic assumption is that everyone can hear each other, can sense the channel correctly. And if they can't, then they have to, again, rely on the receiver. So they would send requests to the receiver and let the receiver notify them whether the channel is occupied. So that sounds familiar, doesn't it? It's indeed connection-based random access. All right, the second question, when to stop? Again, simple, you stop when you finish. But sometimes you can stop earlier if you sense the other ongoing transmissions and know that yours is going to fail. And that's exactly what nodes would do if they are capable of sensing during their transmissions. But if they can't, which is common in wireless communication networks, because usually they cannot, the received signals will be overwhelmed by their own transmitted signals. So in that case, they do not know whether the transmission is successful or not until the end of it. And to avoid wasting a lot of time in the failed transmissions, then again, they will send short requests to reserve the channel first before they start the data packet transmission. So again, this is connection-based random access. But connection-based or connection-free, you always have transmission failures because users do not coordinate their transmissions. And here, the definition of transmission failure depends on what type of receivers you have. And as you can imagine, there are many, many different receiver designs. And one of the most widely adopted one is called the collision model. So here it's very simple. The packet transmission is successful only when there are no concurrent transmissions. you can see this is a pretty much simplified and often pessimistic assumption, because the interference from other ongoing transmissions may not always ruin your transmission. So a more practical receiver model is called a capture model, is that a packet can be successful as long as its received SNR is above a certain threshold. And of course, if you have more advanced receivers, then the transmission failures can be further reduced. And no matter what type of receiver you have, you always have transmission failures. And to resolve transmission failures, back off. That means retransmit later on after a random amount of time. Well, basically, a backup scheme can be characterized by how this transmission probability is set. And a common practice is to set this transmission probability according to the number of transmission failures a packet has experienced. Well, intuitively, more transmission failures indicate that the whole network has a higher contention level. So then to relieve it, the nodes should transmit less frequently. And the examples, typical examples include bioexponential backoff, while the transmission probability will be exponentially reduced according to how many transmission failures that is adopted in Wi-Fi networks, and also uniform backoff adopted in cellular networks. So here we can see there are a lot of design freedoms when we design a random access network. It can be sensing free or sensing based. It can be connection based or connection free. You can have many different backup schemes with all these different receiver models. So numerous random access protocols have been developed. And we also have many different ways to evaluate the performance. And for example, one of the most widely used one is the network throughput. So we know that without coordination, then users' transmissions will collide with each other. And so the number of successfully decoded packets would vary with time. It becomes random. And the network throughput is the average number of successfully decoded packets per time slot, which indeed also tells us the access efficiency. And we know every packet has, it carries a certain amount of information. And in practice, what we care the most is how much information can be successfully delivered. And that is the network sum rate. And of course, we also care about how much delay experienced by each packet. With random access, we know that you may not always be able to transmit when you want, because you have to compete with others. It may take a long time before your packet can be successfully delivered, because you have to wait and retransmit. And another new performance metric that has got a lot of attention recently, which is also mentioned in previous talk, is this age of information. It describes how fresh the packets are, which is determined by not only how the packets are transmitted, but also by how they are generated. So it's very closely related to the queuing delay performance of the packets, but normally you cannot optimize both of them simultaneously. Now you can find many different performance metrics. So to probably evaluate and even optimize the random access networks, you first of all have to probably model it. So as you can imagine, many different analytical models have been developed in the past half a century, but they are usually tailored for specific schemes to tackle different problems. And very often, those differences in the modeling assumptions will need to inconsistent results. So here we can see that basically the random access, or more essentially a multiple access system, can be regarded as a multi-queue single server system. So here, to fully describe a multi-queue single server system, we need this joint stationary distribution of the queue lengths of all the nodes, which is as you can expect, intractable, okay, for most of the cases. And the main challenge here is to characterize the coupled process, queuing processes of all the nodes. Okay? And they are coupled together because they share a single receiver. So many have resorted to a surrogate system called the dominant system. Well, the queues can be decoupled under some special condition. But the difficulty still lies in how to properly set up the dominant system so that it can be analyzed and still statistically indistinguishable to the original system. And another approach which is widely adopted by the majority of the studies, including most classical models that we have learned from the textbooks, is to only focus on the aggregate traffic of all the nodes, okay, by either assuming that the nodes are bufferless, okay, or assume that the nodes queues are saturated. That means they always have packets to transmit. So here we can see by ignoring the queues, okay, the analysis can be greatly simplified, and it captures the essence of the contention from the old nodes. But in practice, we do have queues, okay, to store the incoming packets, okay, and that will need to different performance, okay, under a certain traffic input rate. So here, ideally, okay, we need a scalable analytical framework. While the modeling complexity does not increase with the network size because we have to deal with these massive access scenarios. And on the other hand, we also hope that this framework is unified, okay? Not simplified, but unified, so that all these different random access schemes can be analyzed based on the same framework, okay? Regardless of what performance metrics are adopted. But how to do that? Okay? The big question is, how can we capture the interaction of the nodes, okay, without rendering the model unscalable? And to answer that question, let's look back to this multi-queue single server system. So here we can see that all the nodes, okay, they interact with each other only through their head of line packets. Okay. So in other words, here, the queues are coupled. Okay. The coupled queues are only determined by the behavior, the aggregate activities of their head of line packets. So here, the key is to, first of all, model the head of line packets behavior. And based on the head on package model, and we capture the interaction of all these different head on packets by establishing a fixed point equations of their steady state probability of success. So in general, this head on packets behavior can be modeled as a discrete time Markov renewal process. The state characterization is determined by whether the node sends the channel or not, right? Aloha or CSMA. And the holding time of these different states would be further determined by your protocol design. And here, the linchpin of the whole analysis is the steady state probability of success, okay, of all the head-on packets. And we know that whether a packet is successful or not is determined by, the aggregate activities of all the head-on packets. So based on the limiting state distribution of this head-on packets, then we can establish and solve the fixed point equations of their steady state probability of success in different conditions. Okay? And in various scenarios, we can obtain explicit expressions of their solutions. And then together with this head-on packet model, we can fully characterize the coupled service rates of the queues, as functions of those key backup parameters. All right, so based on the proposed analytical framework, we can do a lot of things. We can characterize the fundamental performance limits, such as the maximum network throughput, minimum mean delay, maximum network sum rates, and the corresponding optimal values of the backup parameters. So here, the backup parameters mean the transmission probability of each node or the backup window size. Okay. Right. And that offers a lot of insights to our practical network design. And one of the examples is that here, in existing transmission control strategies, the tuning of the backup parameters is usually based on fast tracking of some time varying network status. For example, you have to know how many nodes are backlogged or with busy queues or are transmitting. Okay. But that would cause a lot of system overhead on estimation and feedback. Okay. So here, our analysis suggests that, well, here you can do this optimal tuning solely based on the long-term traffic input rates. And you do not have to know those instantaneous network status. You only need to know the traffic input rates, okay, and how many nodes totally in the network. All right, and we have successfully applied the theory to practical networks, such as Wi-Fi and cellular networks. And this is a summary of our series of studies, which you can find in my homepage. And now let's take our focus back to the topic as the comparison of connection-based and connection-free random access. Okay. So the following discussions will be mainly focused on based on my 2 papers, okay? Which you can find all the details online. And that is why I'm going to skip the details and only focus on the final results and the implications, okay, of the analysis to the practical system design. All right, let's rewind a little bit. Okay? So we know that for this connection-free random access, every data packet has to compete with each other. Okay? But for connection-based random access, well, here you send a request first to reserve the channel. Okay. And here we focus on the network throughput. That is the average number of successfully decoded packets, okay, which is also the access efficiency. And to find out the maximum network throughput, this is what we do. We would push the total traffic input rate, okay, keep pushing it. And you will see that the network throughput would first increase with the traffic input rates. And then when the network is saturated, it will be only determined by the transmission probabilities of the nodes. Okay. And then you can further optimize, maximize the throughput by optimally tuning the transmission probabilities. So these are the results. We can see that the maximum network throughput here is only determined by whether nodes sense the channel or not. Okay? And in both cases, they are determined by the successful transmission time and the failed transmission time. And here we can see that the successful transmission time and the failed transmission time would differ, okay, in connection-free random access and the connection-based random access. And also the system overhead will be different in these 2 cases. And that is why we have to take the overhead into account when we evaluate the throughput performance, okay, of these 2. And instead of looking at the maximum network throughput, we would focus on the maximum effective throughput. So that is what is the maximum fraction of time that is spent on the data, only on the data payload transmission. And here are the results for the connection-based Aloha and the CSMA. Okay, so here we can see that they are closely determined by the data packet transmission time and the overhead time for successful transmission and for failed transmission. Okay. And for CSMA is further determined by this sensing time, okay, because nodes have to sense the channel first. And these are the results for connection-based Aloha and CSMA. All right, so now we can put everything together to compare their performance. We know that, well, for this overhead time in the successful transmission, then the connection-based one will be larger because it takes longer time to establish a connection. Okay, so that's the cost of connection establishment. But on the other hand, here the transmission failure does not involve a data packet transmission. Okay, so the failure transmission time can be greatly reduced. And now if we plot the maximum effective throughput, both Aloha and the CSMA case, so this solid line is with connection, okay, connection based, and the dashed line is connection free. Okay. Then we can see that here is in both cases, Aloha and the CSMA, the throughput with connection based random access would succeed, right? Or would exceed the connection free one, right? When the data packet transmission time is sufficiently large. That's pretty what we have been expecting, right? And here the crossing point, right, is indeed the critical threshold we have been trying to find. And we can derive the threshold for beneficial connection establishment as functions of all these overhead parameters in both Aloha and the CSMA case. And we plot them here against the ratio, okay, of the overhead time for a successful transmission in the connection-based case and in the connection-free case. So here we can see that a larger ratio here indicates a higher cost of establishing a connection. Okay. So that means it takes longer time to establish a connection. Okay. And both the thresholds with or without sensing here would increase, okay, with this ratio. Well, that's, again, not surprising, pretty much what we have been expecting, right? Because, well, intuitively, you need a larger data packet transmission time for this connection-based random access to outperform the packet-based random access. Okay, so that's not surprising. But what is interesting here is that we find out the threshold without sensing is much smaller than the threshold with sensing. So how to understand that part? Well, again, recall our restaurant booking example. Right? We know that whether to make a reservation largely depends on how long each customer stays in the restaurant. But here, there is another important factor. Right? That's the capacity of the restaurant. Right? How many customers can be simultaneously served in the restaurant? Well, for a large and a capacious one, it doesn't make any difference whether you make a phone call or not to book a table, because there are plenty of them. Right? But for a small restaurant, then there's a high chance that you probably cannot walk in without a reservation. So here for CSMA, okay, if you sense the channel, then the connection-free throughput is already good enough. Okay, when the data packet transmission time is large, okay, it's already pretty close to 1. So in that case, the benefit brought by the connection establishment is quite marginal. Okay. But for Aloha, okay, if nodes do not sense the channel, then the throughput without connection, the connection-free one, is bounded by E2 minus 1. Okay. And so there is much more room for the improvements if nodes do not sense the channel. And now let's see how to apply the analysis to our practical system design, or more specifically for machine-to-machine communications. Okay. Which one would we prefer, connection-based or connection-free? And recall we have this question list in the beginning of our talk. Okay. So For example, for Wi-Fi networks, it has two access mechanisms. We have this connection-free basic access and the connection-based RTS-CTS access. Okay. So here, to understand which one performs better for machine-to-machine communications, we can first of all calculate the all the key parameters, the data packet transmission time, and the overhead time for successful transmission and the failed transmission, for connection-free and the basic access, and connection-based RTS-CTS access. Okay. And this is an example. Then we can obtain the maximum effective throughput with RTS-CTS, okay, the solid line, and without connection. Okay, that's the basic access, the dashed line. So again, we can characterize this threshold of packet payload length here, okay, which is a function of the data rate, okay, we use to transmit the data packet, and also the basic rate. Here, the basic rate is the rate used to transmit those overhead, those header and acknowledgement, those overhead signaling parts. Okay. So here we can see that this threshold would increase as the data rate increases, because that means the data transmission time is reduced. Okay, or the basic rate decreases. That means it takes longer to transmit those overhead. Okay, so the overhead time would increase. And we can express it as a function of RB and RD, and these are the typical values. Okay. So we know that in practice, the threshold is set to 2 to 14. Okay, so in our current systems. And from this figure, we can see that it's too small. Okay. It should be set to a much larger value, especially when the data rate is large. Okay. And that is often the case in our current systems. And both for basic access and RTS-CTS access, we assume that nodes sense the channel, right? Because it's based on CSMA. Now, if they do not sense the channel, we can still adopt a similar frame structure, okay, by doing some minor adjustments. And then we can obtain this threshold of packet payload length without sensing. Well, again, it is a function of your data rate and the basic rates. Okay. But what's interesting here is that it can be negative, okay, if RD is small or your basic rate is large. So what does that mean? A negative threshold. Okay. It means that no matter how small the packet payload length is, okay, for any packet payload length, this RTS-CTS access, connection-based one, can always outperform the basic access. So this is very different from the sensing-based case. Here we can more clearly see from this figure. So this is the threshold if you have sensing, okay, based on CSMA, then the threshold will be always larger than 2 to 13. Okay. And that is way much larger than the typical values of the packet payload length of machine type devices. So that means this RTS-CTS access will be rarely activated, okay, for machine-to-machine communications. But if you do not have sense, okay, if nodes do not sense the channel, then the threshold will be much smaller. Okay. And for especially when the data rate is null, and you will see that in most cases, your connection-based RTS-CTS access will be better. So how about 5G networks? Okay. We know that 5G networks adopt this Aloha-based random access procedure as the LTE networks, and it has been long criticized for its low efficiency, okay, because of this connection establishment. Right. And so many have been arguing that we should use a connection-free one, okay, to replace it. Well, this low efficiency of the random access procedure is indeed attributed by many factors. Okay? And one of the most important factors is this n-optimized backup parameter setting. So in our current parameter setting, the access efficiency or the network throughput will quickly drop as the number of devices increases. But if they can be optimized, if they can be optimally tuned, then the maximum throughput can indeed remain constant, regardless of how many devices in the network. And also another important factor is this periodic random access slots. We know that users can send requests only at those random access slots which appear periodically. So if they fail, they have to wait until the next access slot comes instead of try immediately. Okay? And both of them would significantly affect the throughput performance. Okay? But here from our analysis, we know that if it's properly designed to achieve this maximum effective throughput, then a grant-based one can indeed outperform this grant-free one, okay, even when the data packet length is very small. Right, so what does that tell us about the access design for future networks? So we have known that it's crucially determined, okay, whether connection-based or connection-free one is good, is crucially determined by whether nodes sense or not. If they sense the channel, then most likely you would choose connection-free access because it would give you better performance. Okay. But if nodes do not sense the channel, okay, then the gain from the connection establishment will be much more significant. Okay. Significant enough to cover the cost of connection establishment. And in general, we have this criterion for aloha. So if nodes do not sense the channel, then the connection establishment threshold is always non-positive. Okay? If and only if this inequality holds. So here, the left-hand side is the overhead parameter, okay, for successful transmission and failed transmission of the connection-based one. Okay? And on the right-hand side is the overhead parameter for the connection-free one. So we know that for successful transmission, then the overhead time for connection-based will be larger than the connection-free one, right, because of this connection establishment. But on the other hand, this overhead for failed transmission, right, could be much smaller than the starter SP because starter SP has to contain the header of the data packet, which is usually much very time consuming. So this criterion tells us that, well, if nodes do not sense the channel, then this connection-based access can indeed outperform a connection-free one, well, specific in terms of the maximum effective throughput for any packet payload length, right? Because here the threshold is non-positive. So for any packet payload length, the connection-based one will be better, right, than connection-free one if their overhead parameters satisfy this inequality. But there are caveats, okay, when we apply these results. Okay? So we know that the access performance is critically determined by your receiver design and your channel models. Okay? And with more intelligent base station design, then the the access failures caused by the multi-user competition can be greatly reduced. And then, well, the benefit of connection establishment could be much weakened. And also, we know that by shifting to this millimeter waves and with all these new antenna technologies, these channel models have been undergoing great challenges recently. So we need to better understand how these new channel models would affect the random access performance. And also for machine-to-machine communications, we know that they have quite stringent latency requirements, especially for URLC, ultra reliable low latency applications. And they also have special conditions, constraints on energy consumption. So by taking into the consideration of all these practical constraints on latency and energy consumption, then our analysis can provide more useful guidance for practical system design for our next generation communications. All right, so this is collaborative work with my former PhD students who are now professors themselves. So I would like to thank them. And everything, all the information can be found on my homepage. Okay, so if you have any questions, comments, I would appreciate a lot if you can send them to me. And this is my email address. Okay, with that, I'm going to end my talk. Thank you very much for listening.
Thank you so much, Professor Lin Dai, for that presentation. And of course, we'll now move on to the Q&A. I believe there have been some questions streaming in as you are presenting all of that. And the first question, Prof, comes from Sharif Hashima. And the question is, how can machine learning help the RAN configuration of M2M networks?
Machine learning. Okay. I guess this question have been asked for many speakers in this workshop. So basically, I think my opinion is pretty much in line with the previous speakers. That is, we need to understand how things work. Okay? Not just to know that it works. We need to know why it works. So that is why I prefer this modeling approach, so that we can understand how to characterize the performance limits and also how to achieve those performance limits. Okay? But of course, machine learning is very, very useful. Okay? And I think it can be definitely used for those dynamic conditions that we do not have good models. Okay? For example, for a completely unknown environment, that we do not even know what the channel model is or what the environment is, then we can definitely try to, first of all, learn the environment, and in the meanwhile, applying all these useful machine learning techniques to optimize or at least try to improve the access performance. Okay. So there are indeed many studies on machine learning techniques, applying the machine learning techniques to random access, because in later, for random access, every user has to determine what to do by themselves, right? Because nobody would tell them what to do. So that's basically a learning process, right? You observe the environment, and then you try to tune your parameters so that the performance can be better. So this can be indeed regarded as a learning process. Okay? But if you have powerful models, then we can better understand how to, learn the environment in the best way. Okay? So in that sense, I guess they are not contradictory to each other. They can be good friends.
Thank you so much for that explanation. And we have another question, Prof, from the same participant. This is again from Sharif Hashima. And the question is, does connection-based consider blockage and channel properties? Does it?
Sorry, what is the blockage?
Okay, the question is, does connection-based consider blockage and channel properties?
Okay, I'm not quite sure what blockage means here, okay. Because it can mean a lot of things. It can be physical blockage, right? That's in the physical layer, or it can be, say, you have a lot of incoming requests and they are blocked. So I'm not sure in which level here blockage means.
Okay, maybe we'll ask Sharif, if you are watching right now. You saw Prof's questions for clarification. So if you could just clarify your question a little bit based on what Prof just said, that will be most appreciated. In the meantime, we'll move on to the next question, and this is from K3P, right? And K3P says, what will be the impact of the packet arrival rate in the overall performance of the network with respect to random access in M2M? What could it be?
Oh, great question. Very good question. So here, yeah, it indeed has a great significant effect on the access performance. Okay. Here in this talk, I only cover this throughput performance. Okay. And for throughput performance, to maximize the throughput, we have to first of all push the input to the limit. Okay, so that is why in the final result, you didn't see the traffic input in the equation, right? Because it's already been pushed to the limits. But if we consider the delay performance, for example, okay, we evaluate the latency of each packet, then the traffic input would definitely play an important role, okay, in the comparison. And use our restaurant booking example, for example, I continuously use it. Say it will make a big difference if you make a reservation when in the peak hour, or when the restaurant has no customers, right? So if the traffic input rate is low, then intuitively probably doesn't matter, okay, whether you make a connection. Probably do not need to make a connection. Okay, but if the traffic input rate is very high, a lot of people are competing with each other, then in that case, it's better to establish connection to reduce the delay. Okay? So this is exactly what we are studying right now. Okay? My PhD students are hardly on this topic. So this is very interesting. Yeah, I would like to share with you about more recent results later on. Yeah.
That's wonderful. Now, the previous question asked by Sharif Hashima, now he's actually been able to expand that. And it says, so the question was, does connection-based consider blockage and channel properties? And this is in regard to transmitter and receiver blockage if the channel between TX and RX is blocked during the connection setup.
I see. Thank you for the clarification. Now it's very clear. Yes, so this is about the physical channel model, right? In the analysis, here we do not consider those, the physical blockage or any interruptions due to the channel fadings. Well, in this comparison, we did not consider it. But in our other papers, so we did consider fading channels, right? So that the channel sometimes is good, sometimes is bad, right? So with all this randomness, then how it would affect your final the access performance, say the maximum throughput or the delay. So if you are interested, you can definitely read more from my papers with my student Li Yitong. Okay, so in those papers, we did consider those more practical channel models. But what we didn't consider is that, as I mentioned in the conclusion part, there are so many changes in the physical layer nowadays. Right? If we, for example, later on have millimeter waves with all these new antenna technologies, then the channel models will be different from our traditional fading channel models. So in that case, then we need to further evaluate the effects of these new channel models on the access performance.
Thank you so much. Hopefully that answered the question. We have another question this time from Ray Ching. And Ray Ching says, thanks for the nice talk. In the model, a steady state probability is assumed. However, for M2M application, the arrival may be bursty and the steady state may not exist. The number of contending users may also be changed with time due to retransmission and backoff. How do you deal with that?
Yeah, that's again a very good question. Yes, of course, with random access, you always have all these dynamics, right? The number of contending users would always change with time. As that's a factor we have to deal with, and also the traffic input rate can be changed. And you also mentioned this burstiness, which is a very good point, that sometimes you have a lot of packets incoming, and sometimes you do not have any packets for a long time. So one of the fundamental assumptions in the analysis, indeed, that the input process is stationary. Okay, so that's indeed a fundamental assumption. But we do have simulations. Okay, we did simulations to find out if the input traffic has certain burstiness. Okay, and then we find out that indeed the analysis can still be applied. Okay, so the reason, one of the intuitive reasons is that even though you have this burstiness of input traffic, okay, but because we tune the transmission probabilities, okay, and the tuning of the transmission probabilities can be regarded as randomizing the input traffic, okay, so that even though you have traffic coming in burstiness, but when you send them, okay, then the burstiness is gone. Okay, because of our optimal tuning of the transmission probabilities. And then you will see that by applying the analysis, you still have this very good match. Okay? So if you are interested, you can definitely read my paper with my student Jiang Wen. Okay? It was published a few years ago, 3 years ago, about LTE networks. Okay, and about the time varying traffic status, you always have users, different number of users contending, that's not a problem. Okay. Here, one of key points that I'm trying to make here is that as long as your objective is long-term statistics, such as throughput, delay, right, is only about the steady state network performance. So as long as your objective is about steady state performance, then the tuning can also be based on statistical information. Okay? You do not need to worry about all this time varying network status. It will be fine, okay? Because your objective is only about the long-term performance. It's not about short-term performance. Okay? So that, I hope that explains your question. Yeah.
Great explanation, and the questions are still coming in. We have another question now from PG Patil, and the question is, very interesting and potential to cover more machines to use available networks. Where is the intelligence to execute located? For example, is it near the nodes, sending machine, or near receiver or aggregator?
Okay, well, I am really excited to have all these great questions. Yes, again, so this is one of the things that I didn't cover in my talk, but has been an issue I'm thinking for a long time. So we are talking about all this about intelligence, right? But whether the intelligence should be at the base station, right, or it should be at the device level. So I guess there have been a lot of debates, but my personal view is that the intelligence, again, my personal view is that should be at the base station, right? The receiver level. And the reason is that we know that the device usually has this energy constraints. Right? They are usually battery driven. And it's also not easy for them to observe the whole environment. Right? But for the base station, right, it has no battery problem, and it can collect information from the whole network. So that gives the base stations this internal advantage of more intelligence, and it can do more control. Okay? But it doesn't mean that it would like the centralized access. The base station does not tell the users when to access. It's not in that way. Okay? But it can definitely collect information and then find out, for example, what is the optimal transmission probability for each node, right? And then you can broadcast this optimal value to the whole network. And then for each device, after it receives this updated optimal transmission probability, then it can still independently determine when to access the network. So it will be interesting, right? The base station get more intelligent, and it can do more optimization, but still the whole network is totally distributed. Right? So that's indeed what we are trying to work towards the future direction. Yeah.
All right, wonderful. I think we still have two more questions from our audience that we'd love to answer. The next one for you, Prof, is a question from Rahul Mishra. And the question is there any change in random access preamble format in M2M communications in case of both connection-based and connection-free procedure?
Yeah. So this is interesting. I didn't think about that, but I think this is definitely possible that you have this network that connection-based and connection-free access would coexist, right? So for some users, probably connection-based access is better, and for some users, connection-free access is better. Then the base station would, do this optimization and see who should establish the connection first. This is definitely possible, but we haven't been looking at it. But this is definitely one of the possible future directions that we would pay attention to. Yeah, thank you very much for this advice.
Great. And I think we just have enough time for one more question from an audience member. This is from Brinda S. All right, and Brinda S asks, what range of frequency band is considered under MM wave communication? Kindly elaborate.
Oh, well, this depends on what system, communication system you are using. Okay? Currently, many communication systems support machine-to-machine communications. Right? As I mentioned, two examples, this Wi-Fi and also cellular networks. Right? So they have different frequency bands, and we also have other standards. For example, LoRa, for those wide area networks standard to support this machine-to-machine communications. But I think many of them would focus on this unlicensed spectrum. Okay? And for unlicensed spectrum, there are two chunks. One is around 2.4 gigahertz, another is around 5 gigahertz. Okay? So the reason that many of them they focus on the unlicensed spectrum is you can see because you don't need to pay for them. Right? So currently, I think it's also a very important research topic that if you have all these different systems, okay, not just a single one, but many independent systems working on the same spectrum, some unlicensed spectrum, because everybody can use it, and then they would interfere with each other. Right? So in this scenario, so how they would affect each other's access performance. So this is also one of our current research topics, is that if, for example, you have both Wi-Fi networks and LTE networks, they both use kind of random access schemes, and then they both work under this unlicensed spectrum, then how to characterize their performance and to find the best way for them to coexist. Okay? So what is the optimal transmission probability, for example, for each system, so that not only they can coexist, but they can even enhance each other's performance. So this is also a very interesting topic. This is one of our papers published last year. So if you are interested, you can definitely take a look at it.
Thank you so much, Professor Linda, and I'm sure many members of our audience will be looking up some of the papers that you've published before. Of course, thank you so much for that very interesting presentation and helping to answer all the questions from our audience as well. Thank you once again, Professor.
Thank you so much. I really enjoyed it. Thank you.
Yes, and we really enjoyed your presence too at this wonderful international workshop. And of course, that was a wonderful way to end our day today. And of course, that brings us to the conclusion of this exciting and eye-opening two-day event. And I want to thank every one of you for attending the international workshop on future communications. Our gratitude and appreciation goes out especially to our generous sponsors. First of all, Huawei International Private Limited, MPIX Innovations Private Limited, Roder and Schwartz Asia Private Limited. We also want to thank the support of the IEEE Communication Society. Now, we'd love to hear your thoughts on our workshop, so please help us click on the link in the chat to fill up a short survey for us, please. Thank you. Now, do also keep a lookout on our website and follow our socials so you do not miss out on the next event. We look forward to seeing you again at the next International Workshop on Future Communications in 2022 next year. Thank you so much. Have a great day ahead and goodbye.